Okay. So, good morning, everybody. I'm sorry about that. Again, didn't even know that was a possibility. And I don't know how that got checked. Look at that. Okay. So, with regard to yesterday, what have we got for questions or anything like that? I know there's got to be some that we want to clear up before we get going.
Is there more class today, or is it Q&A as people have questions?
Well, you can always ask questions.
Understood. Sounds like we have more class.
Oh yeah. If you look at we're about 50, we're about 40% of the way through the book, but we've done a lot of stuff that was kind of off topic, so I don't really mind that.
Okay, cool.
So if anyone has any questions, and also if you look at your name, if you can throw your call sign and information out there, that would be really helpful. So get used to renaming yourself if you haven't done so. And let's see. Okay, any questions from yesterday that I can answer? All right.
Not for the moment.
Okay, so we're going into antennas, which is, as we say, the black art of RF. Okay, let's see if I can do this. I should be able to do a whiteboard. There we go, whiteboard. Screen sharing has failed to start. What happened here? Wow.
Gremlins.
Sounds like you went back to default settings.
I know. There we go. Wow, this is crazy. I didn't change anything.
We control the vertical. We control the horizontal.
Yeah, really?
Yeah.
Okay, well, I'm going to leave from here and I'm going to rejoin. Give me a second, everybody. You know, it's funny because I just tried this a few minutes ago and it worked fine.
Yeah, it worked fine when you were doing it.
Yeah. 441.
I can get my wife up. She's a computer tech.
There, now all I had to do was restart. So that's crazy. All right.
Yep.
All right. So everybody, what we're going to do is we're going to start covering antennas, which again, is kind of like the section that's the black art in ham radio. And in all of electronics, to be honest, antennas are the biggest black art there is. So
notice you say it's an art instead of a science.
It's both. It's actually both. Okay, there are many different kinds of antennas. What's one advantage of feeding directly feeding a random wire HF antenna, and that is that you can experience RF burns when touching metal objects at your station. Okay, so what we're going to do is just start discussing antennas a little bit, and all this will kind of start to make sense. So we're going to draw an antenna right here. This is the kind of like the foundational antenna in radio. This is a half wave dipole. The reason that it's a foundational antenna is that there's a requirement on any piece of wire that at the end, your current has to be 0, which basically means if it's a half wave long, you know that whatever frequency you're at, if it's a half wave long, you start drawing a wave on it. And really this continues on forever. But the important section is that it has a 0 current at both ends. Now I could also draw it like this. And in fact, it sort of oscillates between the two, kind of like a jump rope. But what's important is that it goes up and down, and it's always 0 at the ends. The reason that this is a foundational antenna is that if you look at the center point, if it's a center fed dipole, you basically are feeding it at the current maximum all the time. So if you're feeding it at the current maximum, that means that you basically have the ability to put a maximum current in typically where the voltage is going to be lowest, so your feed point impedance is lowest. Now, it also turns out that if you really want to, the half wave dipole is an important antenna for lots of different reasons. And if you wanted to feed it, let's say right here, you'll still end up with a constraint that the pattern looks like that. But you won't be feeding it at the maximum current point. You'll be feeding it off center and off the current, off the max current. But it still has to obey the laws of physics, which basically means you're still going to have the same pattern. The same thing with this. If I were to feed it over here, I'm feeding it at an even lower current point, which basically means that it's harder to put power into it. Now, if I move it all the way over here and I make it again, that end fed half wave, I'm feeding it at a very low current point, which is a very high voltage point. So my impedance that I'm feeding it at goes up as I get closer to the ends. So because of that, it's very important to understand what is happening at the feed point. The pattern of the antenna will always be the same, but it may become easier or harder to put power into it. And that's why you can have something called a center fed dipole or an off center fed dipole, or you can have an end fed antenna. And they will all work if they're the same length, but you might have difficulty or a challenge putting power into it.
Are there
Now,
any advantages to the other two? It sounds like, why would you want to do this?
well, the big reason that everybody seems to love the end fed half wave, it's still a half wave antenna, is that this is a half wave long.
It becomes a Yagi.
No, it's not. It's just a half wave antenna. It has the same pattern. It's basically a dipole, except you're feeding it all the way at the end. The big advantage is if you have a tree right here, which I'm going to draw in green, right? Let's say you have a big tree over here, and you
Nice
have
tree.
a house over here. It is really easy to put something up in that tree. You don't have to have anything hanging from the center. You can basically just have your end point, one of them at your house, and the other one on a rope up in a tree, and you don't have to be supporting anything like a coaxial cable from the center. So there are a lot of there are a lot of reasons. Go ahead.
Wouldn't that, like you were saying, take more power? Doesn't
No.
that take a little bit more power on the one end, because that would be basically zero?
Right. Well, you
Right.
feed it very close to the end.
Okay.
And again, what's important to know is that your feed point impedance changes. Again, this is something that has been solved. You basically will take this. You have 50 ohms here. And does everybody remember we did a transformer yesterday?
All right.
Impedance match is a ratio of the number of the turns ratio squared. So if I have about 2000 ohms over here and I have 50 coming in, that's 40 to 1, which means I need the square root of 40 for my turns ratio, which is somewhere between 6 and 7. So basically, if I run this antenna, if I run my 50 ohm cable into the primary, and I have my antenna coming out on this side, and I have 2000 ohms, and I have, let's say, a 7 to 1 turns ratio, which is also like a 49 to 1 transformer, typically. And I tie this to a short piece of wire, and this part goes out and becomes my antenna element. It works. That's become a very popular antenna for a lot of people, especially if they're, out camping or something like that and just trying to throw something up in a tree.
Well, that matches them together, but would you need an antenna booster to still bring in what is a weaker signal?
That's it. That's all you need. That transformer does the work.
Okay.
So if has anyone ever noticed that this is a similar kind of thing? Has anyone ever noticed that when you buy a pair of headphones, it has an impedance match, an impedance rating? Headphones can be 4 ohms or 8 ohms or 16 ohms or 32 ohms.
Mhm.
Right? Well, that's the impedance of the headphone. Right? So a lot of stereo systems would have a 4 ohm output impedance.
Right.
And what if you want to match that to a 32 ohm speaker? Well, you would go like this. And your impedance ratio is 8 to 1 or 1 to 8. All right, so here's your in and here's your out. Well, if it's 1 to 8, you need the square root of 8, which is about 2.6 turns. So that would be your turn ratio in your transformer. That would achieve a match between the output of your stereo and your headphones. And that's actually that's an audio matching circuit or audio matching transformer.
Seems like a lot of our education is geared towards learning when we'll need these transformers for our unique situations.
Hmm?
Well, it just seems like we're learning a lot about transformers as if they're customized, because all of us will run into our own situations. You're almost expecting us to build them. That seems to be part of this education.
Well, you can go out and buy one.
Do
I
they
mean,
all come in this amount of variation? And that might be
It
needed?
depends.
Okay.
I mean, you can buy an audio matching transformer for headphones. I mean, if you look at electronic devices, they have them built in, and more than likely you can go find one. And like if you go to Mauser or Allied Electronics, you can probably find an audio impedance matching transformer. You can also go to several different companies that sell radio stuff, antenna stuff, and they'll sell 49-to-1 transformers.
Yeah.
Now you can also wind your own, which is which is educational and fun. You don't have to, but you certainly can.
That's the fun part of it.
I know that's the fun part for some people.
Yeah.
All right, so the next thing we're going to do is we're going to draw this random wire. All right, and the fact that it's random, it means that the length is random. So what we're going to do is draw waves on this random wire. And we're going to take this down to our radio. All right, so we have an endpoint. What is the current at the endpoint going to be?
0.
0. Okay, so that means we also have a voltage maximum right here. And let's see, it goes through a minimum. It's not 0, but it's a minimum. So basically, we're going to end up feeding it at some point where we have voltage and current. Don't really know what it's going to be at the feed point because it's a random length, right? The thing about random length is that it's random. Well, this also means that the feed line becomes a part of the antenna. And when you get down to your equipment, the question is, what kind of voltages are you going to experience down here? Come on. Well, the answer is, I don't really know. But if this is notice the red as I drew is the voltage. Is this red at high or low voltage? Considering this is now our 0 point.
Would be high voltage, wouldn't it?
It would be high voltage. That's right. So what'll happen is you could end up with the chassis of your radio, which you think is going to be grounded, being at some high voltage. Unless there's something isolating it, unless you have forced this point to be at ground, which is 0 volts, and press the issue, the chassis of your equipment could be at high voltage. And I have experienced this once when I put together my very first station. It was on the 2nd floor of my parents' house. There was no ground. I leaned forward to use the mic, and I got a shock from as soon as I started transmitting right on my lip, because my lip touched the microphone. And it wasn't like 120 volt shock. It was an RF burn, basically. It was a little zap because the radio was not grounded. You know, the shield was not grounded, and the antenna itself allowed the antenna allowed the equipment to be at high voltage.
This will be a silly question. Can I ground my radio to an electrical socket ground that is already there?
Good question. Okay, so there's 2 different things. There is an RF ground and there's a safety ground. Okay, so here we go. That's a great question. That was where I was going to go next. So here's your house, and So inside your house, you have your station, let's say right here. And if you look at the grounding in your house, and eventually it gets down to something that goes outside to a ground line, right? To a ground stake.
Yep.
Okay. How long is that wire?
Quite a bit if it's through the house.
Don't really know, right?
Yeah, it's got to go through a lot of other circuits to get back to the box. and
Right.
ground.
Well, it could be direct. It could also be 50 feet long. All right. So let's go into meters. 50 feet is 15 meters long. Okay. So what we're going to do is we're going to simplify this by making a wire, and we're making this 15 meters long, and we are forcing the ground to be at, you know, at the stake, and your equipment is right here. All right. So that wire is 15 meters long. What is the voltage at the point where it's grounded?
0.
It's 0. That's right. Okay. So what is our, let's say we're operating on the 20 meter band. What does my wave look like from one end to the other? Goes like this and goes like this. And how long is that wave?
Be half of it?
Nope.
Oh,
20 meters long. Okay. So what we're going to do with this 15-meter wire is we're going to start drawing a wave. So it's going to go from here up to here and out to here. That would be 20 meters. Where on this is my equipment?
Yeah.
So is that high voltage or low voltage?
I don't.
High voltage. Okay. What is, now here's the next question. What is the wavelength of 60 hertz?
Oh, wow.
Right. So we're going to write our equation 300 F and lambda. Right. This is our conversion equation from frequency to wavelength. Right. But this is in megahertz. This whole thing is in megahertz. So if we have our 60 hertz, that in megahertz would be 0.00060 megahertz. Well, it turns out that if we then have wavelength is equal to 300 million divided by 60 in hertz, we find that our wavelength is 5 million meters long.
Wow.
Mhm.
Right? That's our wavelength of wall power. Right? Our 120 hertz, our 120 volts. So the question is, if that wavelength is 5 million meters long, what does this 15-meter cable have anything to do with that? Absolutely nothing. So for safety ground, that's absolutely fine. How about for RF grounding?
Well, that's the question, really.
Yep. So it's great for safety ground and it sucks for RF ground, which is why they say, depending on the frequency you're on, that's why if you're going to be grounding your station, you want that ground cable to be as short as possible and go directly to a stake in the ground, because it's not, because you're actually performing RF grounding as opposed to safety grounding. You need both. They're both important, but if you have a good RF ground that's really short, it will function very well as a safety ground as well. Where a safety ground does not necessarily function very well as an RF ground.
Need the shortest ground as possible.
Because, yeah, because a ground wire, you know, a safety ground is electrically, you know, fine because it's operating at 60 hertz. An RF ground is not. You know, that will not function well as an RF ground.
Are we talking about a wide braided wire or a heavy gauge wire? What type of, so I'm going to have to run this through the wall to the ground outside, obviously.
It can really be, I mean, it can really be any number of different things. Typically you're going to want something that's, you know, I don't know, at least like an 8 gauge or something. I mean, but don't take that number, you know.
No, but it means I won't go lower than that.
Yeah, well, I mean, you could. I mean,
No, not well for safety. Yeah.
For whatever the safety ground permits, I want to say in a house you can use number 12.
Yeah, they use 12 would be for grounding, like for outlets and such as that. But like what I ran when I rewired my house, I had to put a 200 amp box in. Code required, I don't know what number it is, but
Probably number
copper running
6
from the
or
box to
something.
ground had to be 3/16.
Yeah.
Yeah, solid copper. But what was funny is I was going to ask you is the inspector also had me run it from the box to 3 ground rods, but I also had to run it from the box to a water pipe that was in the ground to my main,
Interesting.
which I didn't understand, but
Well, I guess they
I guess
basically,
it was another path.
they created a ground field,
Right.
basically,
Right.
you know.
Yeah.
Great,
Interesting.
that really
But
helps.
yeah, so ground is not always ground.
I feel grounded now.
Yeah. All right. So now that we've covered that, we're going to cover antennas. See, there's all that foundational stuff that's important. All right. So how long is a half wave antenna? It's a half wave. Okay. So we have our formula 300 and F and lambda. This is always important. That allows us to determine how long our wavelength is given the frequency, or what the frequency is given a particular wavelength. 300 is speed of light in meters per second times a million, really. But because we work in megahertz, we don't really need to do that. So what we're going to do is we're going to say, we look at the first question, and it says 3.550 megahertz. Okay, so it's a half wave at 3.5 megahertz. So what we're going to do first is we're going to take 300 divided by 3.550. So let's see, let's grab the calculator. 300 divided by 3.55, we get 84.5 meters. All right, so that is the wavelength at that particular frequency. So now what we're going to do is, because they said, hey, we want a half wave antenna, we're just going to divide that by 2. 42.25 meters long. Okay, so far so good. Well, the next step is that what we have to do is, if anyone has built an antenna, there's something that in feed, it's 492 divided by frequency. That's a half wave antenna, but this is actually not right. It's actually 468. That's about 5% less. The reason that is 5% less is because of essentially the antenna is a real world thing. If it were an ideal antenna with no resistance and no inductance and no capacitance and no end effects and no no interaction with the real world, the 492 feet would actually work. Instead, the common formula that's been in the ARRL handbook for the last 100 years uses 468. So what we then have to do is take that into account and take 95% of our measurement. So we have 42.25 times 0.95, and we get 40.14 meters. Okay, so then we can multiply that by 3.3 feet per meter, get 132 feet. And if you've built an 80 meter dipole, you know that an 80 meter dipole is 132 feet long. When you do build your 80 meter dipole, you will see that an 80 meter dipole is 132 feet long. So that is how you do this math. So this works for pretty much everything. You know, you can do a 40 meter dipole, a 20 meter dipole, a 10 meter quarter wave vertical. The math is always the same. You have to figure out the wavelength and then shorten it by 5% to get your antenna. All right. Okay, now everybody is going to know this answer already. Okay. If you take a half wave dipole and you move the feed point toward the end, what happens to the impedance?
Increases.
It
Yeah,
increases.
it's
See, and
larger.
right, and we've actually shown why. Because you're feeding it at low right here, and at the end, it's really high. So that's actually one of those questions that, unless you actually draw it out, doesn't make any sense. It just says, oh, well, that's the answer. Well, this is why it's the answer. Now everybody knows that's why it's the answer. So
That
it always,
explains the questions that I always miss.
yeah, and it always comes back to drawing the waves on the wire.
Hmm.
A lot can be solved by just empirically drawing the waves on the wires. What's an advantage of horizontally polarized antenna compared to a vertically polarized antenna? You get lower ground reflection losses. If we were to draw if you were to build a dipole, the radiation pattern of a dipole looks like a donut around the antenna. If it's a vertical antenna, the donut is horizontal. If it's a horizontal antenna, the donut looks like a car tire or a bike tire. Some of it goes up into the sky, some of it goes down into the ground. If you use a vertical antenna and the donut is horizontal, part of your pattern goes down into the ground everywhere you look, because it's symmetric on the in the horizontal plane. Excuse me. All right. What is the radiation pattern of a dipole in free space in a plane containing the conductor? So if we were to look at this is our dipole. It actually looks like this. Looking at it from above. Now, interestingly, looking at it from the side, it would look the same way. So a dipole makes how much energy in the axis along the axis of the wire?
It's on 50% of it. Yeah.
Almost nothing. Right?
It's all vertical.
Yeah. Well, remember that a dipole, if I can draw this in 3 dimensions with any kind of dexterity, the dipole pattern kind of looks like this. Well, this is going to be terrible.
So it's at an angle to the wire.
No, that's not right.
Okay.
It's going to be hard to
Almost
draw.
looked like a Z plane.
Yeah, well, it's going to be hard to draw. So what I'm going to say is, does anyone have a donut this morning or a bagel? If you have a donut, we can use it as a prop.
Sorry.
They're in the
Darn
freezer now.
Okay. So if this is my dipole, basically I have a donut around it. If I have it like this, the donut is horizontal. So if I look at it from the end, it's uniform in all directions because we're basically looking at the donut, coming out like a ring around it. So essentially, if I look at it from above, I see a donut that goes like this and it goes that way and that way. And that's why a dipole antenna is the basis for a lot of other antennas like Yagis, because the pattern is such that some of the energy goes this way, some goes that way, some goes up and down. That's pretty much wasted. If I did it like this, a vertical antenna, some of the energy goes that way and some goes that way and some goes that way and some goes that way. So it's very good for omnidirectional use, but some of it also kind of heads down toward the ground because it's symmetric on this axis. Some goes up and some goes down.
Hence the answer, lower ground reflection with a dipole.
That's right. Because part of the energy goes straight into the ground, but a lot of it doesn't with a dipole. And that's why if you're looking at a dipole, it basically does look like a figure 8. The radiation pattern looks like a figure 8 from above. Right. And again, the stuff that you can't see is the stuff coming up and the stuff going down. But basically, that's what the radiation pattern of a dipole looks like.
Scott, that's only at the feed point at the center.
No, if I fed it right here, it would still be the same because it's defined by the current, independent of where I fed it. A dipole is a dipole, independent of, now, one thing you can have is you can have unequal currents. Depending on, and that's why some people use a thing called a balun, or which is a balanced to unbalanced. If we were to feed it at the middle and we wanted to ensure that even if there was like a tree over here and a house over here, well, okay, so what can happen is that certain things will couple with the antenna, and the two legs of your antenna might not have the same exact geometry. You know, you might have something that, let's say you had a tree available and your antenna actually looks like this. It's actually got a bend. Well, that's not going to be symmetric anymore. So what a balun allows you to do is force equal currents into the two sides. So it gets it to be, for most people and for most installations, it's really not that important. But if you want a cleaner, more predictable pattern, that's what people use a balun for. Okay, if you have a dipole antenna and it is less than a half wavelength above the ground, the pattern is almost omnidirectional. So in other words, you start to lose that figure 8 pattern. You start, a dipole in free space, as it's called, has a nice figure 8 pattern. As soon as it gets up in the air, it starts to have the nice pattern. But if it's lower than a half a wavelength high, the pattern starts to get kind of squished and turn omnidirectional, and you start to lose your directionality. And what happens to the feed point impedance of a half wave dipole as the antenna is lowered below a quarter wave? Below a quarter wave, you get something called NVIS, which is basically most of your energy goes up as opposed to out. It's also known as a sky warmer or a cloud warmer, depending on your terminology. Your feed point impedance goes down, ostensibly because you're closer to ground. And as you get closer to ground, you have more losses directly to ground. So your feed point impedance goes down.
And this is at what? What was the deciding factor? 1/4?
At a quarter wave. A quarter wave ground plane vertical has an omnidirectional pattern in the horizontal plane. So it's an azimuthal omnidirectional antenna. So if I put an antenna straight up and down, this is why we use these on our cars, because when we're driving around, we don't want to have to direct our car, point the nose of our car in one direction to talk to somebody. You know, if we're using a repeater in a car, we want to be able to go this way or turn the car 90 degrees or 180 degrees and still be able to talk. So a vertical quarter wave antenna has an omnidirectional pattern. If we have a 10-meter antenna, which is 28, let's say 28.5 megahertz, we're going to go through the same math. We want to know what a quarter wave antenna is. 300 divided by 28.5 is approximately it's approximately 10.5 meters long. A quarter wave is 25% of that, so about 2.7 meters long. And times 95%, we have to shorten it a little bit. So that's about 2.4 meters long. And we multiply by times 3.3 feet per meter. And we get about 8 feet. So there you go. That's why we have this.
Scott,
Yes.
going back to a little bit higher on page 42, it says if an antenna is less than if an antenna is less than a half a wavelength high, the azimuthal pattern is almost omnidirectional. I assume it's talking about a dipole.
Yeah.
And maybe I don't understand the term azimuthal. I assume that meant 360 degrees horizontal.
Azimuthal is looking from above.
Okay, I guess I'm not finding or not understanding how that we get from that figure 8 pattern to omnidirectional.
Okay, so here's a dipole in free space, right? looking at
Yeah.
it from above. That's its
Right.
azimuthal pattern. And it puts out signal in this direction and this direction. But the
Right,
closer we get to the ground, the more squished it gets.
okay,
And the energy that's directed into the ground is actually kind of forced into that direction, and you lose some of your gain in that direction. So
Okay.
it actually,
You
it
lose your
actually,
loss in the ground.
it actually kind of looks like that.
okay, so it does go in all directions.
Yeah.
Okay,
But part of the problem is that that's true. But if I were to look at it from the side, what I would find is that that antenna would kind of do this.
okay,
And that there'd be something going up right toward the sky.
So
And
that
that's
would
why,
be, that would be what would happen with my case of running an in feed over the top of my house and my garage. It would be
yeah,
absorbed into the house. I would lose a lot into the house.
potentially, yeah. And then the closer it is to the ground, the more it becomes, again, known as a cloud warmer. Because your energy goes straight up and down.
So with a quarter wave, you have to be really sure it's high enough to avoid it being a sky warmer.
So, but if you, so wait, what was the question?
So with a quarter wave, you have to make sure that you're sufficiently above the ground to prevent it from becoming a sky warmer.
Quarter wave is different.
I
Quarter,
thought this was
okay.
the warning about the quarter wave.
So let's talk about a quarter wave antenna. All right, this is our ground. How long is a quarter wave antenna? All right, it's a quarter wave. Well, where's the rest of it? Where's the rest of it? Didn't we say that that the foundational antenna in radio is what? It's a half wave long. So where's the rest of the antenna?
Ground plane.
The ground plane.
Yeah.
So a quarter wave antenna, you need the ground plane. It needs the other half of the antenna. So
That's why the
if I were to
radiating spokes.
Hmm?
That's why the radiating spokes.
Well, I mean, a ground plane can be a pie plate for a very small one. It can be a metal box. It can also be a field of ground wires.
Or it'd be like your mobile antenna with a cookie sheet.
Exactly. Or it could be the roof of your car, depending on the frequency you're on. That might be quite good. So, or if you live near the ocean, this could be the ocean. That's a great ground plane. And the reason that this works is because what you end up having is an antenna that looks like this, which is a quarter wave long. If I were to draw it, what's the current have to be at the end?
Zero.
0. Well, here's a quarter wave. But where's the rest of the antenna? The rest of the antenna is actually down here.
Being absorbed. Yeah.
Well, it's not being, ideally, it's not being absorbed. What's happening is this ground is an electrically reflective surface, ideally, because from the outside world, as far as anyone's concerned, if they're looking at your antenna, they see signal coming from here and signal coming from here. To them, to the outside world, that looks like a ground. I mean, that looks like a dipole. So essentially, the ground is what provides you your other half of the antenna. And in order to do that, there has to be makeup current that flows from the ground. So basically what you end up doing when you put power into it is that you actually induce a current in the ground itself, which is why it's important that that's a conductive surface. If you live on the beach, let's say you live in the desert and this is all sand. Sand is silicon dioxide. It's a really lousy conductor, right? If you just take a ground rod and you pound it into the sand, or 8 feet down or something, that's not going to be much of a ground plane.
Nope.
Not going to work at all.
Nope.
And your antenna will not work very well.
Mm-mm.
And that is why people who live in climates like that, you know, they'll lay down a ground field,
A bunch of ground radios.
Okay.
a bunch of ground radials
Yeah.
to make that surface look more conductive.
Right.
Yeah, that's one of the antennas that was at POTA that we had a couple weeks ago. I think it was Barbara, N7JI. Her antenna, I helped her lay that out, and it's like it must have had 30 or more wires for the ground
Mhm.
plane because of that. Okay. I couldn't figure out why she had so many and other people had so little.
Well, okay, here's a question. Let's say I build an antenna that looks like this. Will it work? If this is a quarter wave and this is a quarter wave,
Yes.
will it work?
Broadcast.
Not a little bit.
Yeah, sure. It'll work. I mean, it's electrically the right length, but now the question is, which will work better? If I take this antenna and put it right on the ground, or if I take this antenna and I somehow manage to raise it 25 feet above the ground.
25 feet above the ground.
And why is that?
That's why reflection more output. And you
Oh,
don't
Well, in
lose-
addition to the radiating element being higher, which is a better antenna? And the answer being that because this is now so far off the ground, there's very little leakage
into the ground.
into the ground. And because ground losses kill your radiation. This will actually work pretty well if it's above the ground. You know, I can improve this by adding another one. And then I can improve it by adding another one and another one. This is actually what I have on the roof of my house. This is my 2-meter antenna. It's a quarter wave and a quarter wave and a quarter wave and a quarter wave. That's
Okay.
my 2-meter antenna.
Yeah, mine's got 3 on it. So
Same, yeah, basically the same thing.
same thing. Okay. All right.
Okay, so this right here, what is the feed point impedance of a half wave dipole? How many ohms?
50 ohms.
That's about 70. It's about 70. Well, it turns out if I have a quarter wave antenna, this is about 36 ohms, which is not a perfect match. What you can do for this is tip the radials down slightly. By doing that, you actually get closer. If you look at this, straight up and down would be 70. So if I tip these down, that's kind of like part way toward having this being just a vertical element. So I actually increase my impedance and I can tip them down, and then that becomes a perfect 50 ohm match.
Okay. That's
So
why some of these small ones, like one I just built, they call it a 45-degree angle bent
Yep.
down.
That's what I have on my antenna. And in fact, I've done antenna modeling and shown that the optimal angle is somewhere between 35 and 40 degrees.
Okay. Yeah, because I couldn't find any information on why we're bending them down.
Yep.
But yet it was a perfect match when I got it done.
Yep, that's why. Okay, so we're on to directional antennas. What HF antenna would be the best for minimizing interference? That would be a directional antenna. The reason being that if you know that you have interference back from somewhere over here and you have a directional antenna that looks this way along the boom, you know that this signal out here is not going to have much effect. If you had an omnidirectional antenna and you're listening to everyone equally from the center point, well, you're going to get slammed by this guy as well. So you're going to be getting that interference. So a directional antenna will, in addition to giving you a better pattern, will limit your interference. Because of something called reciprocity, your transmit pattern is the same as your receive pattern. So if I have an antenna that looks like this, and it has a pattern that looks like this, right? There's my front lobe and my back lobe. That is my receive pattern as well as my transmit pattern. What's nice about that is if I have a gain of 10 dB compared to, let's say, a dipole, which would look like this. If I have a gain of 10 decibels in the forward direction, on transmit, I would have a gain of 10 decibels. On receive, I would have a gain of 10 decibels. So that's why when we're talking about, let's say getting some extra gain, antennas and feed lines come first. Amplifier is the last thing you do, because does an amplifier do anything on receive?
No.
Unless it's got a preamp, the answer is no.
No.
Do
So
I have that rule again?
antennas are always the biggest bang for your buck.
Right, no, but you were saying that before you do any boosting, make sure connections and the antennas.
Yeah,
but-
basically, because you want to fix things that are bidirectional, right? So you've got your transmitter and you've got
Right.
your receiver.
I'm just trying to get you to recite that very nice little summation you had there. You know,
So-
rule 1 and 2 before 3.
Yeah, so I mean, basically you've got your feed line. You've got your antenna. And you've got your connectors. So what you always do is fix your antennas and your feed lines and your connectors first, because those have gain in transmit and receive. It fixes things for both. If you need that, and by putting in, let's say, an antenna that's on a rotator now, you might get an extra 10 dB of gain. There's another way to get an extra 10 dB of gain, and that's by buying a big amplifier, which takes your 100 watts and makes it into a kilowatt. But that amplifier doesn't do anything for your receiver. It just makes you 10 dB louder when you're talking. Improving the antenna will work on both. So that's why antennas are really the big bang for your buck. The same thing with, if you have lousy feed line, you might actually improve your feed. You might actually improve your signal by 5 dB just by replacing feed line with something that isn't weathered or something that has less loss. Same thing with connectors. If you have old connectors that are getting kind of weather beaten and they don't make a good electrical connection anymore, changing those things out can solve a lot of problems. Okay, the next thing we're going to do is cover something called DBI and DBD. Okay, a D refers to a dipole. So I'm going to draw a pattern for a dipole. This has a reference point. Essentially, this is the gain. That is, if we were to draw a circle, this is the reference circle for a dipole antenna. If I were to take a different antenna instead of a dipole that had a pattern that looked like this and a little bit going in the back, I could then draw this circle with this reference point, and this would be 0 dBd. So that's basically, that would be the gain of some antenna circle pattern with respect to what a dipole does. If I wanted to look at the gain with respect to a dipole, I would just figure out what this difference right here is, and that would give me a gain measured in dBd. In other words, dB compared to a dipole. Now, I can also draw this pattern, which is generated by a thing called an isotropic radiator. An isotropic radiator is an imaginary antenna that's omnidirectional in all directions. So the pattern would actually be just a sphere. Or if we looked at it in this plane, it would just be a circle. And this would be 0 dBi gain. And right here, the spacing between dBd and dBi is 2.15 decibels. So it's important to know the difference between something that's measured in dBi and dBd. They're both valid, but they mean a little bit different things. If an antenna has a gain that says that it's 6 dBd, that means that it is 6 decibels better than a dipole. It also means that it is 8.15 decibels better than an isotropic radiator, which again is an imaginary thing. So when you go to build an antenna or buy an antenna, it's important to note how they specify it. They might say that our antenna has 6 dBi gain. If it says that it's 6 dBi gain, that's actually only 3.5 dBd. So if you're comparing it to another antenna that has a gain of 6 dBd, and this one is really only 3.85, and they're the same price and the same size, I'd go with the one that's 6 dBd. Just important to note. All right, so now we're going to look at this green line here. All right, so notice we now have, this is defined as our front side, and this is our back side. So if we were to draw a circle and indicate, okay, this is our back gain, and then here's our front gain, what we would do is we would measure the peak gain on the front versus the peak gain on the back. And we would subtract them from the other. So if this was, let's say, 13 dBd, and this was minus 4 dBd, we'd have 13 minus negative 4 is 17 dB front to back. So that's what a front to back ratio is. It basically tells you how much stronger the main lobe is in the forward direction compared to the reverse direction. So which antenna will have a better front to back ratio, just looking at this,
Yeah, the direction.
versus this? Which antenna do you think will have a better front to back ratio?
The longer one.
The longer one, yep, because there's more directors. So its pattern, if we were to draw it, would probably look like this versus this. So this top one, because it has more elements pointing in the forward direction, in addition to having a higher forward gain, would also have a better front to back ratio. Okay, the approximate length of the driven element. Okay, so we have in a Yagi is a series of one driven element and then parasitic elements. This is the driven element. Usually you only have one reflector, and then all of these in the forward direction are called directors. So
It just keeps amplifying the signal in a sense.
essentially they are parasitic elements. They tend to, the reflector takes the signal that's going backwards and acts as kind of like literally a reflector and forces it back forward. The directors radiate in kind of like in phase with the energy coming in, and they tend to amplify and form a pattern that points the energy more in a directed pattern. So you can have an antenna that's like Cushcraft makes something called a 13B2 for 2 meters, and that has some ridiculous number like 17 decibels of gain. It's a lot of gain. And the way that you do this is you not only have your directors of a certain size, you also have them spaced a certain distance, measured in wavelengths, so that they basically can actually function as a parasitic radiator and push the energy more in the forward direction. And typically, the longer the boom that you have and the more elements you have on it, the greater the gain. At some point, I think there's a point of diminishing return, but some of your satellite antennas, some of your moon bounce antennas could have like 33 elements. There's a lot of gain in those 33 elements. Now, it is also true that the boom length gets quite long when you're doing that. The driven element, how long do you think that antenna would be to operate on a given band in wavelengths?
20 inches?
No, it's a half wave.
Oh, no, halfway. Okay.
Just a half wave dipole, whatever band it is.
Yeah.
That's just a half wave dipole.
I fell back into the Yagi that I built out of tape, which was just measuring it.
So that's a half wave. That's a half wave driven element. The reflector's a little longer and the directors are a little shorter. Okay, next. How would you change the bandwidth of a Yagi antenna? Okay, so if I were to make an antenna and make it out of magnet wire, let's say a 26 gauge magnet wire, it would be very, very lightweight, but it would also have a very narrow bandwidth. If I were to draw its usable bandwidth, it would look maybe something like this, where this is its usable bandwidth right in here. If I were to take an antenna and instead of make it out of 26 gauge wire, I made it out of, let's say, 1/2-inch aluminum pipe. The bandwidth of that antenna might look like this. And that's because of the ratio of diameter to length of the element. Typically, the fatter the wire that you use, or the fatter the element, the fatter the radiating thing, the wider the bandwidth of it, which means you get more usable bandwidth out of the same antenna. Now, the other concern, of course, is that if it's something that's hanging in the air, it's going to just weigh more and it's going to be a lot harder to put up. So there's a compelling reason to not put up, number 3/0 wire, right? But there's also a compelling reason to not put up 26 gauge magnet wire unless it's a very temporary thing. That's why a lot of hams like to use like number 12, number 14, because it's fairly strong, but it also gives you a fairly decent bandwidth. But that's also why Yagi antennas, when you build an HF Yagi, it might be 1-inch aluminum pipe, because 1-inch aluminum tubing, because that gives you decent bandwidth and also some structural support when you mount the thing up in the air.
That's why I'm surprised here that aluminum is so conductive.
Well, yeah, aluminum is very conductive, actually. Aluminum is actually a really good conductor. The problem is, Ray, what happens to aluminum if you leave it out?
Hey, it's going to disappear after a while. Yeah.
It turns very gray and oxidizes. And the problem with
Oxidizes
aluminum is
bad.
that aluminum oxide is not conductive.
Well, especially with a current or anything going through it, it'll be even faster.
So that's why when you build an antenna out of aluminum parts, you have to use clamps, and you use something called like Adelocks,
Right.
which is a corrosion inhibitor and essentially seals the aluminum from the air and water. You can smash two pieces of aluminum together and essentially have a really good connection if you've protected that joint.
Like dielectric and electric circuit.
Yeah. Okay, let's see. How does increasing boom length and adding directors affect a Yagi? It gives it more gain. So what can change the effects of building a Yagi as far as gain, front to back ratio, and SWR bandwidth? You can change the length of the boom. You can put more or fewer elements on the boom, and you can change the element spacing. All right, let's see. How does the gain of 2 3-element horizontally polarized Yagi antennas spaced to halfway vertically apart typically compare to the gain of a single Yagi? Okay, so this is something called an array factor. Let's say that we were to take a single antenna and we look at the pattern and we assume that it looks something like that. Well, if we take 2 antennas and we space them a half wave apart and we phase them, we end up with this pattern and this pattern. Except that in the far field, like far away, what we end up with is that these patterns interfere and they build on each other. And if we do the math on this, we will find that if we space them and phase them properly, what we end up with is not a pattern that looks like this. It's a pattern that looks like this. So we actually, by using 2 antennas and spacing them a half wave apart, we get an extra 3 decibels of gain. And that's why some people will put up a stacked array of antennas. You actually get more gain that way. The advantage of vertical stacking of horizontally polarized antennas. So if I drew my horizontal Yagis like this, that each of them would normally have a pattern that looked like this in the vertical plane. The resultant pattern would actually look like this. It would be a stronger and narrower beam. So it kind of squeezes that beam pattern down, because the energy that goes up and the energy that goes down, they don't do you a whole lot of good. So by adding those in a vertical plane, you basically eliminate those and squeeze them in toward the main lobe.
And the question again had been, ask the question again, please.
What's the advantage of vertical stacking of horizontally polarized antennas? And what it does is it squeezes the radiation pattern in the vertical direction. And because you're trying to get stuff out in the horizontal direction. Now, what we really need to do is explain a little bit about why we're doing this. So what we're going to do is draw the ionosphere. And let's say that our goal is to talk over long distances. So here's our antenna system. So which direction of radiation? I'm going to draw one in red, and then one in yellow, and then one in green, and one in blue. Which direction of radiation will give you the greatest distance when it bounces off the sky and comes back down?
The lowest one.
Yep. Okay. And that is why everybody aims for a low angle of radiation if they're looking at long distance communications. So the closer you can squeeze your signal down in the vertical direction, the greater the range you can cover. The same is also true on VHF, except that you just basically are aiming it toward the ground. So there's two ways to achieve this. You can change your antenna, and what's the other thing you can do, which a lot of people can't?
Height?
Yeah, you can build your property. You can buy a property on a mountaintop.
Mhm.
In which case, your takeoff angle, you might have the option. You can do that. You can do this. You can do this. You can do that same blue line. But, oops. You also have the option of doing this if you're up high. So height is the best thing you can do for an antenna system. And that's why people like to go mountain topping, because that gives you the ability to aim even lower because you started off higher. Okay, which of the following is an advantage of using a gamma match with a Yagi antenna? So a gamma match is interesting because it does not require that the driven element is insulated from the boom. You can actually have it attached as a metal connection to the boom of the antenna. It doesn't seem that it would work, but it actually does.
Is it important to know how it works?
Well, I mean, if you look at it, what it really comes down to is the fact that, let's say that you have the boom, the antenna boom, that's the thing that has all the elements on it.
Right.
Right. And a gamma match is such that if this is electrically connected, how can you actually make current flow on this element if they're all connected? And the way that you would do that is you'd basically have something that feeds a voltage away from the center. And by feeding it away from the center, it's important to remember that wavelengths are, you basically will draw your current pattern like this, right?
Yeah.
Well, if the voltage is zero, if the voltage is very low right there, and you feed it off center, you still have current fed here. Even though it's a solid thing, it's the same basic idea as the fact that your wire for your ground is not ground. It's taking advantage of that. Like if you were to look at something called a shunt fed tower, let's say that you have just a tower that's stuck in the ground, right? This is very typical of AM radio. If you were to try to isolate this from the ground on an AM radio station, you would need to actually take this insulator at the bottom and have it supporting all the weight of that giant tower, which is 300 feet high. which is not really something that you want to typically be doing. So what you would do is you'd feed this at the ground and you'd have another feed point up here. And that basically says, okay, I'm going to feed it right here. I know that the bottom is at 0 volts, and I'm going to actually inject a signal into the tower above that point. And I know that because it's not, even though it's connected, I know that because of this physical distance, ground is not ground anymore. You're taking advantage of that situation. That's why antennas are a black art.
And a very similar question is, we've got a Yagi that has essentially the driven link isolated from the others, and the others are at ground, and yet they're somehow making a gain back to the driven link.
Right. And that's because the boom is essentially similar to ground.
Okay. All right. What can you say about a disc cone antenna? Primarily a receive antenna, but how does it work?
You can transmit on them too.
Pardon?
You can transmit on them too.
Okay.
So a disc cone antenna is something that looks like this. It's literally a disc on top of a cone.
Okay.
And if there's a center axis of symmetry, it's omnidirectional. And if you want to think about it like this, essentially what it is a I went through a derivation of this once. And essentially what a disc cone is that each of these parts of the cone can function as different length things. So essentially, like, the upper part can operate as one section and the bottom part operates as a section.
Mhm.
And it's kind of like an upside down vertical, kind of. But because it's sloped outward, it functions on a lot of different frequencies. Like, you can have a single antenna that operates from 25 to 1300 megahertz and
Okay.
has a decent SWR in that entire range. What you give up for that is gain. You basically have no gain. But
Okay.
it works on a very wide range. But you
Good.
essentially have zero gain.
All right.
And that's why people like to use them for scanners, because they can operate, on a very wide range of frequencies equally well. Okay, let's see. What is a beta or hairpin match? A shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. That's called a hairpin or a beta. How long is each side of the driven element of a quad? A quad antenna is a full wave loop, is the driven element. So if it's a full wave loop, that means that it's a quarter wavelength on a side. So a quad will actually look like this, kind of like a Yagi. So that would be a quad, where you have one driven element and reflector and directors. Same kind of deal. Now you can have a 2-element quad. You can get rid of the directors altogether. And because it's a loop, you basically end up with a lot of, you end up with a little bit of gain compared to a dipole. It's a full wave loop. The full wave loop is going to be a little better than a dipole.
This would be all the same size now?
The director is going to be about 5% bigger. Or sorry, the reflector is about 5% bigger.
Okay.
And that's always true. If it's a Yagi,
Mhm.
Your reflector is about 5% bigger. Same thing.
Okay.
It's about a 5% increase in size. All right, specialized antennas. The name of a dipole with a single central support. This is known as an inverted V. It's a very common antenna because you can basically pull up the center point and your feed line, which might be heavy coax, is pulled up from that point. And then you can tie this point and this point to just about anywhere. And because the current is maximized at the center, well, you still have your high current point, which is what launches your signal outward at a pretty high point. So an inverted V is a very popular antenna. Now, the other problem with that, of course, is that your voltages maximized at the end, which means that if this is close to ground, you might have some leakage to ground. So you typically don't want that actually on the ground. You want that above the ground. The other thing is you don't want the ends somewhere where somebody can touch them.
Now that would also be directional, right?
That's directional in the forward and reverse direction. And you also have some signal going upward. So it actually is a good antenna because you lose a little bit of gain, but you gain coverage.
Okay. Now that if you're using something like that now,
You can also do a sloper.
consider on the direction that you place it, right?
Yeah.
It will be somewhat directional. Okay.
Yep. You can also do a sloper, which goes upward to one side more than the other. Like it wouldn't have that much radiation in that direction. Combined vertical and horizontal polarization of a multi-wavelength horizontal loop. If I were to draw a horizontal loop and make it really big, that's almost omnidirectional with a low radiation angle. So if I have lots of room on the 160 meters, I put up an omnidirectional loop, just a really big loop antenna. What describes a log periodic? A log periodic antenna is a wideband antenna. Does anyone remember what a TV antenna looks like?
Yeah, basically,
Well, but this is what a TV antenna looks like. And notice it has very long elements and very short elements. A log periodic has low gain, but wide bandwidth. And that's because on any particular, and all of the elements are typically driven. And what ends up happening is that on any given frequency, only 2 of the elements are active because the other ones are so far away from resonance. So on one particular band, it may actually be just these 2 elements. On another band, it may just be these 2 elements. So you really have just like a whole bunch of 2-element antennas that are logarithmically related to each other. And because of that, you end up having very, very wide bandwidth, which is great for a TV antenna where you're trying to receive a whole bunch of different frequencies. Very wide bandwidth. Let's see, NVIS is near vertical incidence skywave. That's NVIS antenna, again, is a very low antenna. So this is used by the military a lot. So let's say you have an antenna that is 3 feet above the ground. Well, we said that most of that, and for a really, really low antenna, most of the energy will be directed upward. If there is a helicopter up above, that's great. That's what you want. So that's known as NVIS. For long distance communication, it's not so good, but for very local communications, mostly upward, NVIS is very good for that. And it stands for near vertical incidence skywave. A beverage antenna. A beverage antenna is also known as a traveling wave antenna. You would typically have it long and in one direction and very, very close to the ground, let's say 6 feet above the ground. And this is multiple wavelengths. And the way this works is that as a receiving antenna, so if it was fed here, you'd have a very strong receive pattern just in that one direction. It's a terrible transmitting antenna because it's so close to the ground. You'd lose a lot of energy toward the ground, but it's a really good receiving antenna, largely because it's so directional. So let's say you have a killer 160 meter station, you have hundreds of acres to put out lots and lots of wire. If I'm looking from above, I have antennas that look like this. And I have a switch where I can basically rotate, where I can switch to any one of those antennas. And somewhere in the center of all of this, I have a big 160 meter antenna, like a vertical. Because when I'm transmitting with the vertical can also pick up tons of noise. These beverage antennas are directional, but they're terrible transmitting antennas. The vertical is a terrible receiving antenna, but a great transmitting antenna. So if I am able to switch back and forth between transmitting and receiving antennas, I have a killer station. The disadvantage of a multi-band antenna, we talked about image rejection yesterday. If I have an antenna that is cut for one frequency, and we'll say that this is a half wave on some band, right? That actually has a frequency response that looks like this. And it's for that one frequency. If I have an antenna that now looks like this, I have two separate elements. They operate on two different bands. My frequency response of that antenna now looks like this as well. If I had another band, it would have another frequency response. That signal, even if I'm only listening for this one on my radio, the signal that comes in on this one can actually get into my receiver and desensitize my radio. So it relies on your radio to do a better job. So a multi-band antenna has poor harmonic rejection because it is designed to be multi-band. It allows lots of things to come in. The purpose of an antenna trap is to permit multi-band operation. A trap, here we go. This is a trap. Okay, what does that look like, everybody? What are the two things you see?
Capacitor and inductor.
Capacitor and an inductor. The frequency of the trap is 1/2 pi square root of LC. Well, here's my C, here's my L. And because they're in parallel, the frequency response looks like this at that frequency, which basically means it serves for that frequency as the end of the line. So if I have an antenna that has a trap right here, this section at a given frequency will be the only section that is working at that frequency. For all other frequencies, the energy passes through as if nothing's there, and the entire length of the antenna can be used. And again, this is known as a trap. It literally traps the energy and says, nope, that's the end of the line for that particular band. So the reason to do this is, if anyone has heard of an antenna called like a Hustler 4B TV, it's a 4-band trap vertical. There's a trap, there's a trap, there's a trap. You have, for instance, a 10-meter section, and this is a 10-meter trap. Then you have a 15-meter section. So up to 15 meters, this entire length is in use. And then you have a 15-meter trap. And so by placing those traps at the right point, you can actually make an antenna that's resonant on multiple frequencies by essentially cutting off the rest of the antenna. So this would be a 10-meter trap. This would be a 20 meters. And let's say this is a 40-meter section. So on 40 meters, the entire antenna is resonant. On 20 meters, just up to the trap is resonant, which is why tuning of these things can be a little challenging, because the trap has to be at the right frequency and at the right place.
Yeah, those are pretty short too. If I remember right, W7PL10 told me about one of those when I'm, because I'm still looking around, and it was actually somewhat short. It wasn't really a big antenna.
The reason that it's short also is what's inside a trap. An inductor, right?
Inductor.
And that inductor can actually function as a loading coil as well.
Oh,
for those
okay.
sections above. A loading coil basically makes an antenna physically shorter and electrically longer. So you can actually, in fact, has anyone ever heard of a slinky antenna?
Oh yeah.
Ever used a slinky?
Yeah. I'm gonna try to make one of those too, just for the fun part.
Okay. This is a slinky antenna. So this could actually be a 40-meter antenna that's 12 feet long. 40-meter half wave. The whole thing is basically coiled up. Now, do you lose something in efficiency because of all these coils and the interaction of the coils? Absolutely. But if the coils don't short out, then you have a functioning antenna.
Mhm.
And this whole thing would basically function as a loading coil, which is a shortening device. Feed point impedance of an end-fed half-wave antenna, again, very high. It's about 2,000 ohms. In which direction does an electrically small loop have nulls in its radiation pattern? Okay, so electrically small is less than 1/5 of a wavelength. And really, it's actually closer to like 1/10. So it's kind of weird. This radiation pattern goes out in these directions and virtually nothing up or down. So if you've ever heard of a mag loop antenna, that's an electrically small antenna. If it's horizontally laid out, it's actually going to be omnidirectional horizontal. If it's vertically oriented, like this, you're going to have nulls in this direction. So you're not going to have, you're going to have no energy going through the center of the loop, which is really interesting because it actually works really well in that direction. So you can actually take that loop antenna and you can rotate it and actually have some directionality. And what's cool is that you might have, like I have one that I use in a hotel room that's 3 feet in diameter and it works great on 20 meters. A screwdriver mobile antenna. A screwdriver basically looks like this. And by having this section in the base, essentially what I have is a coil with a piece of a shorting material, which is a beryllium copper finger stock. And I take this entire element and I raise and lower it driven by an electric cordless screwdriver on a screw thread. And this is actually fixed. The finger stock is fixed. And this is actually connected to the bottom of the antenna. So as I raise and lower this, what ends up happening is that the coil, which is connected to the top of the antenna, shorts right there. And by raising and lowering it, I use more or less of the coil. And that's known as a
You're just
screwdriver.
tuning it in a sense.
Exactly. You're changing the length of the loading coil to tune the antenna. So basically you're varying the base loading inductance to change the length of the antenna.
Okay, so that's basically the same antenna then that if you were using an alligator clip, except
Yep.
it's doing it electrically. Okay.
Exactly. Okay, what's the maximum direction of radiation from a portable VHF UHF halo antenna? A halo is something that looks like this. And that I have one for 6 meters. I have one for 2 meters. It's got an open point right at the end. So I can draw it like this. There's a capacitor right there at the end point. And this antenna actually is omnidirectional in the plane of the antenna. So this is a great little antenna for omnidirectional work and and it's actually horizontally polarized. So it's very good for long distance communications. You can actually, I've actually seen these, you can actually stack halos. And what will stacking of antennas do?
3D.
Oh, increase.
By 3 dB in the horizontal plane. You could actually stack more of them. You could actually stack 4 of them. And that would give you even more gain in the horizontal plane.
If there's 3, is it 6 dB or is it
It's
4.5?
a little bit less, yeah. Okay, radio wave propagation. Let's take a 5-minute break and then come back to radio wave propagation. Everybody good with that?
Good with that.
Okay. Hey, Mike. Oh, you're muted, Mike.
Yeah, go ahead.
There we go. Yeah, I take an alpha loop or a homemade mag loop everywhere I go when I travel. I use a little Yaesu FT817 and it has a microphone. I've got a little portable code key, and I've got a Signal Link USB and a laptop, and I operate low power from inside a hotel room.
Yes. So it's a homemade antenna.
Yep. Or well, I actually have one that's homemade and one that I bought from somebody from I think it was Alpha Antenna.
Oh, I know them, but they're expensive.
Yeah, but I got it secondhand.
Yeah,
And
okay,
it came
fair
with a tripod and everything.
Yeah, those antennas running about $500.
I think I paid about 200 for mine
Yeah.
with the tripod.
Yeah.
But they work great. I mean, again, you have to temper your expectations a little bit.
Well, it's better than it's something that's better than nothing.
Right. And
The compromise on gain.
but the thing is, you compromise on gain, but they have very, very, very high Q.
Yeah, it's narrow bandwidth as well.
But they're tunable. And because they're tunable, the bandwidth is incredibly high or incredibly low, and the peak is really sharp.
But you can move it.
Yeah, you can get away with it pretty well.
Yeah.
And what you give up with that is that if you have the portable version, you can't transmit with any more than about 10 watts because the Q is so high that
the voltage is
the
incredible
capacitor in the
capacitor.
box, even at 10 watts, has about 700 volts on it.
Yeah. Yeah, that's the problem. One of the problems.
I'm okay with it. It's inside a box.
Yeah.
Hey, Scott, we talked about, what's the advantage of a bow tie?
A bow tie is very similar to a disc cone.
Okay.
If you look at a
I
bow
figured
tie,
it's just inverted.
it's rotated 90 degrees.
Right.
Right. Basically, because a bow tie is one of those things that it's the way that it's built is that it flares.
Mhm.
It's very broadbanded, which is
Okay.
why they're used for TV antennas.
Right. I just read an article on one and thought, well, that's kind of strange, but
There's no reason you couldn't use it as a transmitting antenna. You just have fairly low gain out of it too.
right.
And you'd have to do impedance matching and
Yeah.
all right, we're on to radio wave propagation. All right, sunspots. What is the significance of the sunspot number? Higher sunspots usually indicate that there's more ionizing radiation coming out of the sun. More ionizing radiation coming out of the sun means that it makes the ionization levels in the atmosphere higher, in particular in the F layer, which is what gives us long distance propagation. If we were to draw the atmosphere, we would see that in the upper atmosphere, in the ionosphere, which starts at about 30 miles up, we have the D layer and the E layer and the F1 and the F2 layers. So here's us way down here. The E layer starts at about 100 miles. The F layer starts at about 200 up to, let's say, 600 miles. So as the sun passes overhead, we basically receive a constant bath of ionizing radiation coming out of the sun in the form of cosmic rays and ultraviolet and X-rays. Different rays penetrate to different depths. As they do, some make it down to the surface, most get filtered out. The density of each layer gets higher as you get closer to the Earth. What you end up with is that in the D layer during the day, you get very high ionization levels because there's fewer and fewer things to ionize up in the upper atmosphere. You have very low ionization levels. But what that also means is that the ionization that forms in the upper atmosphere has very few things to recombine with. So essentially the formation is slow and the disappearance is quite slow. Well, down in the lower atmosphere, where the density of the atmosphere is very high, during the day, you basically have this really thick layer that forms. And it turns out that because that layer of ions is so heavy, what ends up happening is that energy that gets up into this layer will typically get absorbed by one of those ions or one of those electrons, and that energy is transferred to the adjacent atoms. So basically it heats up the sky. This is what AM radio does during the day, because this works up to about 10 megahertz, which is why during the day, you can't hear anything below about 10 megahertz up from long distances, because the signals that would travel long distances, they get up into the D layer and the energy is basically just absorbed. Higher frequencies will pass through, and depending on the level of ionization in the upper atmosphere, the F layer, that will determine whether or not that energy passes through or gets absorbed and re-radiated downward and in other directions, essentially bending the waves. The higher the level of ionization, the higher the frequency that works for, right? So this has very profound consequences, because that might mean that if we look at 28 megahertz, that means that 28 megahertz requires a lot of ionization. 14 megahertz, which is the 20 meter band, does not require so much ionization. And because the sunspot cycle, basically the sun, goes in 11-year cycles like this, that's known as a sunspot cycle. We're actually right about here right now. We're on the rise. Basically, what we end up with is that we have peaks and valleys that are 11 years long, where you have sunspot peaks and sunspot valleys. That translates to solar radiation peaks and solar radiation valleys, which translates to ionization peaks and ionization valleys in that upper atmosphere. What that means is that at the peak, we have 28 megahertz, which is the 10 meter band. That's really pretty good and very, very fun. At the bottom, the highest we'll sometimes go is the 20 meter band, which is 14 megahertz. Right now, we're up to about here. So during the day, sometimes you get 21 megs, which is the 15 meter band active. And an occasional, occasionally we'll get 28 megahertz, which is 10 meters. At the peak, hopefully the 10 meter band will be good every day, because that's actually a lot of fun. What typically happens then also is that you get this diurnal effect, which is day to night, where you basically end up with this stuff in the lower atmosphere, in the D layer, forming very quickly during the day and disappearing very quickly at night. Which basically means that at night, this whole filter disappears. And all those low frequencies below 10 megahertz can make it up there into the upper atmosphere. And there's usually enough ionization up there to catch those frequencies and bend them back down, which is why at night you have 80 meters and 40 meters and 160 meters still active, right? Whereas during the day, they don't really work. Okay, so high sunspot numbers indicate a probability of good propagation at higher frequencies. The solar flux index, or SFI, is a measurement of the amount of ionizing radiation that's coming out of the sun at 2800 megahertz. And that's measured every single day. That's also known as 10.7 centimeter solar flux. At what point in the solar cycle does the 20 meter band support worldwide propagation? During the daylight hours, that would be any time, because it rides through the low parts of the peaks, the low parts of the cycle. And even when we're at the peak of the cycle, well, 20 meters is still in there. It still works. So 20 meters is kind of like the workhorse band on the air.
Now that's where when you're NHF, that's really critical to follow that, to see when it would be best, for what you pick up frequency wise.
And even like right now, the solar flux is about 120. Earlier this week, it was 180. And it's predicted to drop down to below 100 in the next day or so.
Is there a site that gives you those readings?
There are many sites.
Okay.
If you just look up solar flux index,
Okay.
there are, I mean, this is a big part of space weather, as it's called. And it allows you to predict a lot of things that are happening.
Yeah. That's
So
what I was wondering, because you've talked about that before,
Mhm.
like in the TechNet on different things, and you've given those numbers out, and I'm thinking, well, what the heck is that? So now I know.
yeah, so so basically, when the solar flux was at 180 during the day, 10 meters and 15 meters were alive.
Mhm.
Even at night, 15 meters was still pretty good to Europe, which is awesome. Yesterday, the solar flux was 120, and 20 meters was good into your 20 meters was good, and 15 was so. Today, 20 meters is great, and 15 is not so good, right? The solar flux is down around 100. So basically, when the sunspot numbers are really good, you start to see 10 and 15 meters open up. And there's also another band called 12, which was given to us in about 1980. That's a relatively new band. So, but at the bottom of the sunspot cycle, you can go for months and months and months and never hear a single thing on those bands. Even if you listen every day, you can hear, you'll get nothing. What causes HF propagation to vary periodically in a 28-day cycle in addition to 11 years? That would be the fact that the sun is rotating on its axis, and the sunspots that are on the surface of the sun typically form groups. The sunspots themselves are very often correlated with high levels of ionizing radiation, so that when the sun rotates, those groups are aimed toward us or not. When they're not aimed toward us, we typically don't get much in the way of radiation. When they're aimed toward us, we do. And as they come around, we get in the window again. And those groups can last for long periods of time. Let's see. Let's say the sun has an X-ray flare or solar flare. How long does it take for that to get to Earth?
For about
And
8
that is
minutes.
8 minutes. So, unfortunately, we don't usually have any warning that it's coming, because it's coming at the speed of light. And it takes 8 minutes for even our satellites to see that there's something coming. So the satellite might tell us at the exact same time we're about to be hit by something that we are hit by something. And so these ultraviolet and X-ray radiation from solar flares can cause sudden ionospheric disturbances. Basically, all that energy being dumped into the ionosphere at once can really, really screw things up and cause very high levels of absorption and noise. So typically, that will cause even more absorption on lower frequencies than higher frequencies. But I have been on the air when something like that happened. Has anyone else ever experienced it? You're on the air and all of a sudden you think that somebody disconnected your antenna. All the signals go away. What happened? It's like somebody flipped a light switch and it's just noise and nothing else.
Unplugged you.
Yep, literally unplugged. How are radio communications usually affected by charged particles that reach Earth from solar coronal holes? So basically, that's in addition to the sun throwing ultraviolet and X-rays at us. Sometimes it'll throw particles at us, charged particles. We are always in something called the solar wind, which is a stream of charged particles. Sometimes it'll get worse if there's a little hiccup that comes out of the sun. That takes about between 20 and 40 hours to get here. So we do have warning. That's often known as a coronal mass ejection or a CME. When something happens like that, we typically will start to get HF distortion on the HF bands, and it will do some serious damage to our ability to communicate.
Just a crazy question. Would that be, like I say, how does that handle if you're up in Alaska for like the Aurora Borealis?
It's worse. At the same
Yeah.
time that we get an
Big
aurora,
big time then. Okay.
yeah, the same time that we'll get an aurora, you'll typically have some serious damage, to, well, and it's not always the case. A lot of it depends on whether, on the polarity, believe it or not, of all the particles.
Okay.
If, depending on the polarity, they could either go around the Earth and not interact with us, or they could directly interact with the magnetosphere and be drawn in and then start to rip our layers apart.
Okay.
And depending on which one happens, that determines whether we get an aurora. That determines whether or not it starts to cause, temporary damage to the layers of the ionosphere. And if the ionosphere basically ends up bouncing back and forth, that's noise. That's also absorption of signals, and we can see we can see HF disturbed for a couple of days from something like that. What benefit can high geomagnetic activity have on radio communications? Okay, a geomagnetic storm is basically, we have our geomagnetic field. When we get a blast of particles from the sun, that can cause, again, the auroras, that can cause our geomagnetic sphere. NASA has been watching this forever. Because what ends up happening is that you end up with, well, the atmosphere can actually expand a little bit, which can cause satellites to slow in orbit, cool stuff like that, which can cause satellites to then crash into the ground. So it's actually really important to NASA to watch these things. And that's why there's this thing called space weather. We have two indices called the A index and the K index that have come along with the solar flux. The K index is a measure of how disturbed our geomagnetic sphere has been for the last 3 hours. The A index is like an accumulation over the last day. So the K index is really like a real time, how screwed up is our atmosphere right now by the sun.
What was the transit time again for the CMI to Earth?
For which one?
For the CMI, coronal mass injection.
Oh, CME is about it's 20 to 40 hours. Think of it as like, a day. So once we know that it's coming, we have 20 to 40 hours to try to, limit the effects. But, it's the sun. What can you do? One interesting thing that happens when the aurora starts to improve, starts to become visible, is that VHF signals can actually be bounced off the aurora or refracted off the aurora. The 6-meter band is actually very popular with auroral scatter. Now, at the same time that happens, if you've been on HF, if you think about, for instance, talking from here to Europe, from the West Coast to Europe, you basically have a path that goes over the North Pole. It follows essentially the same path that you would take when you fly to Europe. That's the shortest route. What ends up happening is that when the aurora becomes disturbed, you start to see the aurora borealis. The signals that you listen to coming over the pole are all warbly and distorted. So at high latitudes, your HF propagation will start to go downhill, and you start to have very distinct sounding signals coming over the pole. The K index is the short-term stability of the Earth's magnetic field, and the A index is the long-term stability, like within a day. Okay, so now we have maximum usable frequency and lowest usable frequency. Okay, the maximum usable frequency is also known as the MUF, or the MUF as it's called. Basically what you end up with is levels, you end up with ion clouds, which have a certain density way up in the sky, in the ionosphere, typically in the F2 layer. The higher the level of ionization, the more dense the cloud is, the higher the frequency it can reflect back down or refract back down. So it will cause the signal to bend back down. So if this cloud is not very dense, you might have a signal that passes right on through. It might be that if the cloud is over here, this signal will pass on through, but another one will get refracted back down. Now you also have this angle of incidence. You have a steep angle and a shallow angle. That also comes into play. There's a lot of geometry up there. Maximum usable frequency is the highest frequency that will provide communications between 2 points. The LUF, or the LUF, is the lowest frequency that will provide communication between 2 points. So the maximum usable frequency is affected by where the sun is, if it's directly overhead, or it's still nighttime, or it's morning. The path distance and location, certain angles might work better than others, and solar radiation and ionospheric disturbances. So if the sun is throwing particles at us, then kind of all bets are off. If we're having an X-ray flare and the level of ionization goes really, really high, maybe that'll work well. Maybe that won't. Okay, what happens to radio waves that are below the MUF and above the LUF? Okay, so here's our MUF and here's our LUF. And we have from 0 to infinity frequency. Well, if something is below the MUF and above the LUF, we're in that nice little intersection point, and radio energy that is thrown up at the ionosphere will come back down to Earth. So that is a nice big check mark. Now, what happens with radio frequencies below the lowest usable frequency down here? They are usually just sucked into that D layer and will be absorbed. We never see them again. Frequencies that are above the maximum usable frequency up here, those will typically just shoot up into space. And we'll never see them again. So there are also instances where, remembering that the maximum usable frequency can vary and the lowest usable frequency can vary. You could actually have an inversion on a given path where the LUF is here and the MUF is here. And what would happen at that point? You would not have any path via skywave to get from point A to point B. It just doesn't work. In other words, your maximum usable frequency is now lower than your lowest usable frequency because of the geometry and because of the conditions of the atmosphere and because of the path that you've chosen. So that won't work at all. So for, let's see, which of the following applies when selecting a frequency for lowest attenuation when transmitting on HF? We're going to eliminate this particular case. So the best signal that you'll typically find is something that is very close to the MUF, but slightly below it. So if the MUF is 22 megahertz and we want to optimize our communication distance to a certain point, and we know that the MUF to that point is 22 megahertz, what we're going to do is we're going to share this right here. If I can find it. Here we go. Okay, so we just determined that the MUF is 22 megahertz. What frequency would we pick, everyone, of all these different bands? We want to be just below it. Which band would you like?
17?
Well, that would work. What's an even better choice? I'd go there. I'd pick 15 meters. because we're right below 22 megs. We're between 21 and 21.45. So it might turn out you try that and it doesn't work. And then what's your next choice? Then you go down to 17. Okay. What's a reliable way to determine if the muff is high enough to support skip propagation between you and a distant location? There are beacons that are out there that rotate around from place to place on the planet. They each have their turn at transmitting. And they are transmitted on a variety of different frequencies. So if you listen on those published frequencies, you can pick out which beacon is transmitting and whether or not you're able to hear it on a particular band. If you're able to hear it, and it's, for instance, South Africa's turn to transmit, and you're hearing it on a particular frequency, you know you have an open path to South Africa. A characteristic of skywave signals arriving at your location by both short and long path. Okay, so there is something called a great circle. And so here's the Earth. And if we're going between this point and this point, there are two ways to get there on this sphere that are the most direct, that radio waves travel. One is the short path, and one is the long path. Sometimes you will have paths that work at the same time. So what is the difference between the short path and the long path in this case, if they both work, everybody?
Length.
Time and distance. That's right. The Earth has a circumference of about 24,000 miles. In radio time, radio waves travel at 186,000 miles per second, which is about 1/7 of a second per trip around the Earth, which is about 140 milliseconds. So if one path is, let's say, 4,000 miles, and the other path is 20,000 miles, you will have a distance of 16,000 miles, which means that you will actually hear an echo of about 100 milliseconds between the two signals that you're listening to. All right, next, ionospheric layers. Where do ionospheric layers reach their maximum height? Basically, they expand upward when the sun is directly overhead. The layer that's responsible for most of the really fun propagation that we have is known as the F2 layer. Again, we have D, E, F1, F2. Any idea where the A, B, and C are? A, B, and C were left in case anybody ever found them. Never found them. So D, E, F1, F2. F2 is the one that's responsible for all the fun propagation. The F2 propagation, because it's much higher than all the others, this is typically good for about 2,500 miles in one bounce. So how would you manage a contact between the West Coast and Europe? One, two, double hop. How would you get between here and, let's say, the West Coast and Indonesia? One, two, three. And between here and Antarctica, which I've done. This is very cool. Let's erase that. One, two, three, four. Now, the tricky thing is that every time it hits the ground, you lose some signal. Every time it refracts off the sky, you lose some signal, which means that, as it turns out, that along this path, the muff has to be suitable and the luff has to be suitable to carry that signal. In addition to that, you can't have so much loss at one of these points because it's hitting off of some surface that absorbs energy that the signal gets completely destroyed. The signal that gets to the other end might be this much power. All right, so that's 1 picowatt. That's one billionth of a watt. It's very likely that the signal that your radio is receiving, time to take a moment and say, oh my God, this is some amazing technology, has that much power in it, and you're actually able to listen to it. When your transmitter power was 100 watts. This is how much is actually making it to the other end. Your loss along the way is minus 140 dB. That's the path loss that you're experiencing. Yet it's still able to be received. This is amazing tech that allows this to work. Okay. So
Any sufficiently advanced technology is akin to magic.
that's right. Okay. In the E layer, we're going to redraw the E layer. So D, E, F1, F2. The E layer is a lower altitude. And because it's a lower altitude, it's responsible for skips of about 1,000 miles. They say 1,200. We'll put down 1,200. You can have something called sporadic E, which is, even though you don't expect heavy levels of ionization to occur, you get really, really dense ionization. And this, which is sporadic E, can be responsible for propagation that's up to 144 megahertz, which is the 2-meter band. So it's really good for 50 megahertz, which is the 6-meter band, and for the 2-meter band. But this is very sporadic. And that's why it's called sporadic E. But for instance, Oregon to Arizona is a path that actually works on what's normally line of sight. Sometimes. Very hard to predict. That's why 6 meters is known as the magic band, because every so often magic happens. The ionospheric layer that's closest to Earth is this annoying D layer, which absorbs signals below 10 megahertz. And it's during daylight hours because of the sun energizing the layer. And this is why, again, we can't receive AM radio signals during the day from 1,000 miles away. Okay, critical angle. Critical angle is the highest takeoff angle that will return a radio wave to Earth under specific conditions. So here's the critical angle. If that works, and at some point it doesn't work anymore. So this right here is the critical angle. A type of propagation that allows signals to be heard in the transmitting skip zone. Okay, so a skip zone is basically, we have our transmitter and our receiver, and we're bouncing our signals up like that. Well, the thing is that this angle right here is above the critical angle. So is this, so is this. By geometry, this would put signals right back down here, or here, or here. Well, so this is known as the skip zone. But it is possible to hear signals, because when the signals get up here, most of the energy gets refracted back down, but some of it goes out and hits stuff, and some of it will scatter back into this area. And we'll actually have something called scatter that allows you to hear things in the skip zone. It's typically a lot weaker, but it is actually possible to hear stations. It's not very easy to work them, but it's possible to hear them. And because of that, the characteristic of HF scatter, because it's very sporadic and piecemeal, it has a very wavering and fluttery sound. In addition to that, to get back through the skip zone, it is possible that energy will travel on this path, and this path, and this path, and a few others, in which case it arrives at different times. If it arrives at different times that are continually changing, you end up with constructive and destructive interference, and you end up with louder signals and quieter signals, and that basically sounds like this, and a lot of distortion. Okay, amateur radio practices, station operation and setup. Okay, station operation and setup. What is the purpose of a notch filter found on a lot of transceivers? So what we're going to do is we're going to draw our frequency spectrum, and we're going to put a whole bunch of different signals. And we're just tuning our radio so that we're picking this one up. We're listening to that one station. Sometime in the middle of this, somebody else is tuning their radio and it lays down a signal right there, right in what we're listening to. Well, a notch filter would basically allow us to tune like that, a notch, so that we can basically say that if there's a signal there that we don't want to hear, we can actually block it out. Now, if there's anything there that we do want to hear, it'll block that out too, which is why we don't just go using a notch filter all the time, but it allows us to basically take away a carrier signal or a very strong signal that could be interference from what we're listening to. That's called a notch filter. Okay, IF shift, intermediate frequency shift. So what we have now is we basically have these things called mixers in our radio. We did that yesterday. It looks like this. And we are allowed to tune and filter things. And here's a filter. And then we can have another frequency range filter right here. Maybe we have a really complicated radio that has a first IF and a second IF, and then a detector. So this would be a double super hat receiver. Some of them are actually triple. They actually have 3 individual stages. What they then can do is allow you to have a filter in the intermediate stage and another filter in the intermediate stage. And these can be tunable, or you can change this frequency a little bit so that this filter appears in a slightly different place. And what that'll allow you to do is, for instance, take that offending signal and change your receiver so that your receiver filter is now right. Oh, come on. Your receiver filter is now over here. And this is now the blue signal, which is annoying, is now outside of the receiver passband. And that's known as IF shift, to allow you to reduce signal overload due to strong incoming signals. And that relies on our ability to build a receiver that has a tunable intermediate frequency, or IF. How does a noise blanker work? A noise blanker looks for that annoying signal, and if the signal is a repetitive pulse noise, for instance, so it could be ignition noise, pop, 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 pop. It's something that if it's a periodic signal that occurs in one place, you can actually set up your receiver so that it picks up the frequency that it's occurring on. And when it's occurring, it knocks down the gain of your receiver, thereby making this a lot less annoying. And because they're typically going to be of short duration, it allows your receiver gain to come back up so you can still hear what you're listening to. What happens is, as the noise reduction control level in a receiver is increased, noise reduction is kind of like an adaptive way of handling all of this. So if you do something to knock out the noise, the problem is that if the noise is sufficiently loud compared to what you're really actually supposed to be listening to, you're distorting things to the point where the noise is going away, but you're also distorting what you're trying to listen to also. So if you turn your noise reduction up too high, I personally hate noise reduction because I find myself, being not really liking what it does to what I'm really listening to. But sometimes it really helps. But for the most part, I do not use it. But that's just me. The purpose of an electronic keyer, well, if I were to draw a Morse code key that looks like this, here's our code key, and here's our contact, and here's a hinge right here. And when we push down, it completes a contact, right? If we push it down for a half a second, we get a half a second. If I push it down for a quarter second, I get beep. Depending on how fast I do that, that determines whether or not my transmitter turns on and turns off in a particular pattern, which we now know, which we know as CW or continuous wave. The code that we use to encode CW, encode information using CW, is known as International Morse. And at some point, your wrist gets sufficiently tired to the point where you just don't want to do it anymore if you're sending really fast. So what we then do is we use a nice little piece of electronic magic called a keyer, where you basically have two different inputs into an electronic device. And one is a DIT input, which is a short, and one is a DA input, which is a long. By doing this and closing two different switches, the keyer has an output which closes a circuit in the pattern that you've told it to do, which is a combination of DITs and DAWs, so that all you have to do is close the two switches, DIT and DAW, instead of actually tapping out all the timing itself, which allows you to go a lot faster. That's known as an electronic keyer. The device that you use to do this is known as a paddle in most cases, where you have one finger doing DITs and the other finger doing DAWs. You can go a lot faster that way. One advantage of selecting the opposite or reverse sideband when listening to the radio. Okay, so that obviously does not work if you're listening to single sideband, because if somebody is transmitting an upper sideband signal and you start listening in lower sideband, the speech will be inverted. But let us say that instead of this blue signal, I am now trying to listen to this yellow signal right here. And a red signal comes on right over here. So the way that upper and lower sideband work is that, for instance, I'm now listening to lower sideband and the red signal is in my passband. Now I'm going to switch because I'm listening to Morse code. Morse code does not matter which is upper and lower. And now I switch to the upper sideband and voila, the red signal is no longer in my bandpass filter. So just by switching the sideband, I've basically given myself the ability to eliminate that offending signal. That
Is that
works very
same
well on
just
Morse code.
tuning up a little bit? Like if he was
Yeah.
transmitting on 7, you could try to listen on 7.005.
I could move up slightly, but the problem there is that then the pitch that I'm listening to would change. And if I try to match my pitch to the transmitted signal, then I would then be off frequency. What is meant by but this is a way to fix that. So there's something called split. We're going to talk about something called split mode. So split is where your receiver and transmitter does anyone remember what a transmitter receiver pair looks like? Mike, don't you know what a Collins is, Mike? 32S1 75A4. You're muted, Mike.
I used to have a Drake, the same deal.
TR4 or T4R4.
Yeah, that's that pair. Yeah.
Okay, so it used to be that you used to have a transmitter and a receiver, and you used to have a switch, a TR switch in between them that would basically take the antenna signal and switch it between the transmitter and receiver. Well, you could have a separate tuner and you could have a separate tuner here. So which means those could be on different frequencies. Those, if they're on different frequencies, that's known as split operation, where you're transmitting on a different frequency than you're receiving on. Well, in today's radios, it is very rare to find a split receiver and transmitter. So you have this thing called a transceiver or XCVR, which has a receiver and a transmitter built into one box, which is a great thing because you have the TR switch internally. It handles all that for you. It happens really, really fast. But what that also means is that because it's all computerized, let's say that you want to be transmitting here and receiving over here. Okay, why would you ever want to do that? Well, let us say that I was lucky enough to be operating from, oh, let's say Elephant Island in the South Atlantic, which is an uninhabited place. And here is my transmit frequency, and everybody in the world is pointing at me at the same time, trying to get heard. If I was trying to listen to signals coming in on that exact same frequency I was transmitting on, I wouldn't hear anything and nobody else would hear me either. So what I then do is I say, I am listening. Whoops. I am listening up 3. So I will say I'm listening up 3. So this is 3 kilohertz. And I will say I'm listening up 3. So everybody will start transmitting somewhere else. I might say listening up 3 to 5, in which case all their transmitted signals are now coming in a range where I can actually change my receiver frequency and listen for one particular one without trying to pick out one from the entire mess. So this is known as split. It's very useful if you have something called a pileup.
Yep, good fun.
It is a lot of fun. Which of the following is common for use in a dual VFO feature on a transceiver? And that would be to permit monitoring of 2 different frequencies. So it might be that if I am the hunter of this station, I'm listening for this station. And I also want to figure out where that guy who is on Elephant Island is operating, where he's listening. And I have a second receiver and I'm able to hear my local station that's talking to him and know that that station is right here. Okay, well, I now know where I want to transmit because I know that that station on Elephant Island just picked this guy up right there, which means I'm going to try to piggyback on that other station and get heard. What's likely to happen if your transceiver's ALC is not set properly when transmitting AFSK? That's frequency shift keying signals, like teletype. All right, so when you're transmitting data, your signals kind of look like this. If it's audio frequency shift keying, you're going to transmit on any of those different frequencies. If you're driving your transmitter too hard, and your ALC is your automatic level control. If you're transmitting and you have your drive turned up too high, your signals when you transmit will end up over here as well. Not just where you want them. And then people will start telling you that your signals are all over the place and hey, knock it down because you're wiping out the band for everybody. I've had it happen. I've received that phone call. Not a fun phone call to get. Okay, let's see. What can be a symptom of transmitted RF being picked up by an audio cable? Okay, so let's say we're doing computer stuff and we have our computer and we have our transceiver. All right, so we have let's say we have multiple lines. We have our PTT line, which are push to talk. We have our receive line and we have our transmit line. Okay, every piece of wire can function as what, everybody?
Antenna.
An antenna. That's right. So if there's stray RF in the shack, what can happen if that stray RF gets onto this line?
Bad things.
It drifts into your computer. That's right. So the Vox key doesn't unkey the transmitter. The Vox circuit doesn't unkey the transmitter. The transmitter signal is distorted and frequent connection timeouts. And in some cases, your computer can lock up, which is always really annoying and embarrassing. Because if you're in the middle of trying to have a conversation with somebody and you're trying to work, for instance, the country of West Xylophone for the first time ever, and it's the only time you've ever heard West Xylophone on the air, and this is your big chance, and you got a report saying, okay, here's your signal report, and you try to key back up and confirm it, and your computer locks up or reboots, you just lost it. So very important to take as many RF chokes as you can and put them on all the signal lines. I have on my USB cable, because my computer, my radio has a sound card built in. I have a USB cable that handles everything between the computer and the transceiver. I have 5 RF chokes on that cable. I have 1, 2, 3, 4, 5. And the reason I have 5, why do I have 5?
The more the merrier.
Because 4 wasn't enough. I tried 4. I tried 3. 3 wasn't enough. 4 wasn't enough. I needed 5 to stop the problem. So, okay, what's the correct amount what's the correct adjustment for for the load or coupling control of a vacuum tube power amp? Okay, you want to maximize your power output without exceeding the maximum plate current. Okay, so what are the 3 things in a triode tube? We have a cathode,
Yeah, cathode,
Emitter and a
we have an
grid.
anode,
Plate.
and we have our grid. All right, and sometimes there's actually a heater. So what happens if we maximize our current? If we, let's say that this anode is rated for 800 milliamps, and we have tuned it and we're delivering 1200 milliamps through the anode. What happens to our tube? It gets really hot. It gets really hot. You might actually vaporize something at some point. So what you want to do is make sure that you don't overdrive your tube. You don't put too much plate current in. My first radio was a Kenwood 520S. It had a pair of 6146Bs, and they had a total plate current of, I believe, about 200 milliamps at 800 volts DC. So you do the math, that's about 160 watts. That was a 100-watt transmitter. You wanted to make sure that you never went over 200 milliamps, because that would destroy your tubes. What reading on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? Well, this plate, you basically have a tuning control, which is capacitors and inductors. You want to match what's happening out here to the outside world. Vacuum tube transmitters are really, 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 what's the word for it? They're hard to kill, to be honest. They're very forgiving. And by basically having a tuning circuit, that actually works something like an antenna tuner. It doesn't exactly, but it kind of does. It basically matches your circuit and allows you to make sure you're not running too much power, too much current. So the way that you would do this, you would adjust your tuning circuit and you would look to dip your current, your plate current. Because you don't want to, you basically, once it's tuned, you end up with a dip in the current.
The transistors are much more vulnerable. They can burn out, and they don't
Yeah.
handle high loads.
Yeah, exactly. You can kill a tube. Basically, the way that most electronics die is by overheating. You can kill a tube by overheating, but it's really hard to do. You can kill a vacuum, you can kill a transistor by overheating pretty easily, which is why there's, the early solid state amplifiers, they died frequently because they didn't have a lot of protection circuitry built in. It's really hard these days to kill a semiconductor because the amplifiers have so much protection built in. They have thermal protection, they have overcurrent protection, they have SWR protection. Because the SWR protection keeps you from trying to dissipate power back in the transmitter. So they actually will fold back through the microprocessor, they'll actually fold back the transmitter power to keep the heat dissipation and voltage at a safe level. ALC, automatic level control. If you're using a power amplifier, you want to keep your ALC from overdriving your tube. Again, because if the ALC doesn't stop it from happening, you can overdrive it. If you overdrive something, you basically can end up with self-oscillation. You can end up with spurious emissions, harmonics. Basically, you can end up with a lot of distortion on your signal. And a distorted signal, there's no point sending it. So what condition can lead to permanent damage to a solid state RF power amp? If you drive it too hard. Basically, if you put too much power into it and there's not any protection protecting it, you'll drive it too hard and you'll blow something up. Why is a time delay sometimes included in a transmitter keying circuit? Well, what did we say was inside every radio? And sometimes if you had two radios, you had an external one. What is that thing in the middle?
Oh, filter?
TR.
Nope, it's a TR switch.
Oh, okay.
Because these things use a common cable, right? They use a common antenna. Well, what happens when you transmit if there's a path through the antenna back to the receiver? What happens to your receiver?
You'd overdrive it.
Yeah, you blew up your receiver. So basically, that TR switch is a very, very important thing. It is really important to do the changeover between transmit and receive in an orderly fashion so that when you switch over, because in a transceiver, this is all in one box, to make sure that when you transmit, that receiver is disengaged, to make sure you're not dumping anything into the receiver. What type of device is often used to match transmitter output impedance to an impedance not equal to 50 ohms? That would be an antenna coupler or antenna tuner. Okay. We're into test and monitoring equipment. The advantage of a digital voltmeter compared to an analog meter is that it has better precision. Knowing that something is 3.22 volts may be important to you. Why is
Scott?
high input impedance
Scott?
desirable? Yeah.
I have a question.
Yep.
On my voltage control, they tell me to be at 13.8, and yet
Mhm.
even though it's digital, it tends to wander a tiny bit up into 13.9 and 14. Is that causing any problems for the radio, or is it within
No.
tolerance?
That's fine.
Okay.
If you look at actually, if you take a voltmeter and put it in your car and watch what your battery does, a battery, if you've left it discharged, is down to 12 volts. When the system's under full charge, I'll sometimes get 14.5 volts, and everywhere in between. And actually, you'll get depending on how much current you're pulling, you'll get a little bit of voltage change as well.
Right. On this one, it has a set point at 14.0 volts. In other words, I could just put it to that and it'd be fine.
Mm-hmm.
Okay.
I'd leave it at 13.8 and just let it drift a little.
It's sort of hard to dial in. It drifts a tiny bit, but yeah.
Yeah, I wouldn't worry about it.
Okay.
Why is high input impedance desirable for a voltmeter? The whole concept of observing the function changes it. Basically, if you have a high input impedance, that means you're basically looking at it without changing it as much as possible. As much as is possible. If you have a high input impedance, let's say megohms, basically by Ohm's law, you're going to be drawing very, very little current out of that circuit to actually measure anything. When might an analog readout be preferred over a digital readout? If you're looking for tuning a tuned circuit, you basically are looking for a dip in the meter. It's easier to see a meter go like this than to see numbers change. Sometimes having that meter, like on an antenna tuner that I have, when I'm adjusting my tuned circuit, I go watch the SWR and I want to see the tuner. I don't really care what the number is exactly. I just want to see it do this. And when I get to the bottom, I know I'm good. I don't care if it's this close to the bottom or this close to the bottom. I just want to see it go from high to low. Item of test equipment that contains horizontal and vertical channel amplifiers is known as an oscilloscope. The great thing about an oscilloscope is what can we do? For instance, if we hook it up to our wall voltage, what can we see?
Voice pattern?
You can see, well, if we're, yeah, you can
Wait.
see our peak to peak voltages, right? You can't, you won't just know what your
Highs and lows.
RMS voltage is. You'll see your peak to peak voltage. If you look at your voice, you can see voice peaks. Let's say you're looking at your RF output signal. You can see whether or not if you're sending like with Morse code, what your attack time is on your signal. If it's too steep, you'll get distortion. Don't want that.
In my case, I just hooked it up to my speakers and can see the RMS values and the wave at the same time.
Okay, good. The best instrument to use when checking the keying waveform of a transmitter is an oscilloscope. If you're using Morse code, you want to see that again, it's not too steep of an attack. A steep attack makes a clicking sound. What signal source is connected to the vertical input of an oscilloscope? When checking the RF envelope pattern of a transmitted signal? Well, we're basically looking at this. So this is time, and this is amplitude.
There's
So-
voltage over time.
Voltage versus time. So basically the attenuated RF output of the transmitter goes into the vertical axis and time is on the horizontal axis. This allows us to see what the pattern actually looks like.
Scott, all of a
What
sudden,
is
there's been a whole series.
attenuated?
Attenuated, okay. So let's ask this. If I have a signal that is right here, here's the signal going up, right? And I have a tap in here. And inside here, I basically have this, and I have, let's say, a 1 meg ohm resistor. Is that going to matter much to the 50 ohm impedance of the transmitter or the antenna?
No.
Not really. But does that mean that there is no signal coming out through here?
No.
There's a little bit, right? If I were to take this and let's say that it was the right impedance, and I take this and I stick it on my scope input. And honestly, I'd probably put it through a capacitor as well and use that for my oscilloscope, my vertical trace. And I would then have a sampled version of what was out here, but in a much smaller copy. Because it would have had to go through the 1 meg resistor to get there. You know,
Okay.
and I might actually put a resistor here as well and use some kind of voltage divider and make sure the voltage didn't get too high, something like that. So basically, that would be just like a sample port.
But
And
it
I
might
would-
be worth mentioning how much oscilloscopes are now down in price, especially from China.
Yeah,
Whereas before, I mean, I have a $500 scope that, you know, from Tektronix or Fluke would have run 5,000, and it seems perfectly adequate, maybe even better.
you can get a really nice digital storage scope for a few $100s now.
Yeah, Antec is a good one.
And I do have an old tech scope, so, but
I
it's
used to
from,
work there. Yeah, as a TNI
Are-
engineer. They used to test the measurement over at Tech. Yeah.
so I actually have a 454 that was one, I was born 1 year before it.
We put out the first 386 computers that would capture waveforms and analyze them on a card into a computer versus the actual scope. Instruments on a card.
Okay, let's see. Which of the following must be connected when an antenna to an antenna analyzer when it's being used for SWR measurements? An antenna analyzer is basically a tiny little transmitter that is an unlicensed transmitter. And so you hook up your connector to it that goes up to your antenna. And what this allows you to do is vary the output frequency from, let's say, 1 megahertz up to 35 megahertz, or sometimes this might be up to 350 megahertz and allows you to sweep different frequencies across and measure what the SWR is. And once you've done that, you can then plot a graph of SWR versus frequency that looks like this, which is completely not legal to do using a real transmitter. But because this antenna analyzer has an output of something on the order of 1 milliwatt, and it's very, very sensitive in measuring its return power, it is legal to sweep from, you know, any frequency to any other frequency. Very, very useful tool. The reason that it's so useful is, let's say that you have an antenna and you're transmitting into it, and here's what you found for your SWR in the band that you're allowed to transmit in. All right, well, that's good, right? But let's say that the SWR that you got looks like this. Okay, what's wrong with the antenna? Damned if I know.
Yeah.
If I were to be able to look outside, I could either see that there's a dip right here, or there's a dip over here. Well, if this is plus frequency and this is minus frequency, it's really kind of helpful to know which side the dip is on, because that determines what I do with the antenna. If it's over here and it's at a high frequency, that means the antenna is too short. If it's over here on the left side, that means that the antenna is too long. That completely changes my response, does it not? On how to fix things. So that's why an antenna analyzer is so useful.
What's the average cost on one of those?
You know, it's really interesting. You can get a nano VNA, which can function as an antenna tuner, for under $100 now.
Yeah,
Oh.
those coming from China, they're terribly cheap. They're advertising them all the time.
I know. And, you know, do they work? Yeah, mostly.
It would give you an idea of where you're at.
Yeah.
Well, you got through 2 or 3 of them to find one that really does work.
That's right. The other thing you can do is you can get a, something that's like an MFJ analog tuner that is probably about $200, which works very well. It doesn't give you a complete graphical representation. There's another company that's called Rig Expert. That makes completely digital tuners. They give you a nice little graph, and something like that is probably $400 or $500.
So basically, if you use an SWR and one of those, that would give you a better idea. I've got an SWR that's 3, 4. I could slap that on it, and then that would give me an idea of where the problem would be at.
Well, I mean, ideally you can not even do that at all. You can just use the tuner in the first place.
Oh, okay.
The tuner will tell you where it is.
Okay.
Or the antenna analyzer will tell you where the problem is.
Okay.
The nice thing about the little nano VNAs and some of the more advanced ones is that if you have a problem in your cable, they can actually do time delay refractometry as well, and send a pulse down your cable, and you can figure out how long it'll tell you how long it takes for the pulse to get back to you, and it'll tell you where the defect is in your cable. Pretty cool stuff.
Great.
Not a lot of money.
Yeah.
What's a use for an antenna analyzer other than measuring the SWR of an antenna system? You can determine the impedance of a coax cable. If you put a 50 ohm dummy load at the end of a cable and you say, measure my impedance, it will tell you what the mismatch is. If you know what the mismatch is, you can figure out what the impedance was. When making measurements on an antenna system with an analyzer, if you have a strong transmitter nearby, remembering that an antenna analyzer is a tiny little transmitter and receiver. If you have a strong transmitter nearby, it can actually trick your analyzer into thinking that there's more signal coming back than is really coming back. Which of the following can be what can be determined with a directional watt meter? A directional watt meter is basically a watt meter with a couple of diodes in it that allows you to determine whether power is traveling this way or this way on a feed line. If you have an antenna up here and you have a transmitter here, this would be the forward power and this would be the reflected power. By going through and using a couple of little calculations, if you can say, okay, this is 72 watts and the reflected power is 12 watts, you can plug that into your equation and figure out what the SWR is. If you look at something like an MFJ watt meter, like this, let me share that. Keep coming back to it because this is one of my favorites. No, I don't want to spin now. Okay, so notice we have this cross needle. We have actually two needles right here on this meter. One is for forward power and one is for reflected power. Those curves that are in between them, I don't know if you can see that or
Yeah,
not.
they're clear. Mhm.
They're clear. Okay. Well, the curves indicate, based on where those needles meet, what the SWR is. Essentially, what they're doing with those curves is they are doing the mathematical calculations based on those 2 meters.
We want both needles going to the far right, if I see this right.
Yes, that is correct. You want 0 reflected power.
All the way
But
to the right.
all the way to the
gotcha.
right. You want the reflected power lying flat.
Got it.
That's exactly what I do. But basically, let's say that you can't do it. For whatever reason, you can't find a match that gives you a perfect match. You can't find positions for the two capacitors and in the inductor that give you a perfect match. So you have it so that there's an intersection on the 1.5 curve. Well, it's an SWR of 1.5. Depending on how much power you're running, that might be okay.
But you still want the idea of 1-to-1, yes?
Ideally, you want 1-to-1, but sometimes you can't get it. So just to know that, and be able to look at the graph or to be able to look at the lines and figure out where the intersection is, it's actually quite helpful. Because then essentially what it's doing is, this is a directional watt meter that's doing the calculations for you without actually having to require you to pull out the paper. Okay. Which of the following instruments can be used to measure relative RF output when making antenna and transmitter adjustments? You can use something called a field strength meter. For instance, you put your transmitter into the key down mode and you walk around using a field strength meter that tells you how strong the RF energy is in that spot. So if you make 100 different measurements by walking around your property, you can kind of get an idea what the field looks like. That would give you the radiation pattern. Another way to do that would be to dummy up the antenna as best you can using modeling software and run a model which basically predicts what the antenna pattern should be. Reality is always a little bit closer to reality, but still a model is usually a good start. What type of transmitter performance does a two-tone analyzer test? That would be linearity. Essentially, if you put two different non-harmonically related audio signals into a transmitter, you want to see that they are not somehow interacting with each other. If they are, and you get intermodule and you get distortion, that means you have a transmitter that's acting in a non-linear fashion. Ideally, we want linearity. Let's see, interference with consumer electronics, grounding DSP. Okay. What sound is heard from an audio device or telephone if there's interference from a nearby single sideband transmitter? Has anyone ever done that to anyone?
Oh, yeah.
Yeah. Okay. I used to do that all the time. My parents had a stereo and they could tell when I was on because they'd hear
Now
even if the stereo was off, they could hear that.
when you're out late at night, you call your parents on the phone. That's what you do.
Yeah. Okay, what's the effect on an audio device when there's interference from a nearby CW transmitter? You'd hear clicking or humming. Now, it used to be that when there was something called a wired telephone that was owned by the Bell system that you rented from them, because you used to actually have to rent your phone to use it. You'd plug it into the wall. If you said, I'm getting distortion from a ham transmitter, they would actually come out and give you a filter, essentially a bypass capacitor. So which of the following might be useful in reducing RF interference to audio frequency devices? That would be a bypass capacitor, thereby taking the RF and splitting it from the audio frequencies and taking the RF and shunting it to ground so it doesn't make it into your speaker, for instance. Another way to do that, to eliminate common mode noise or no interference caused by common mode current on an audio cable, would be to put a ferrite choke around it, which would permit the audio frequencies to pass and take the RF frequencies and burn them up as heat. Okay, ground loops. Ground loops are really important because we're going to make a little bit of a drawing here and say, okay, so let's say here's our transmitter and our transmitter is grounded. Then we have a device over here, which is our tuner, which is grounded. Okay, and now we have a computer, which is also grounded through the power cord. Okay, now what's important to note about all these different grounds?
They're all far away from the,
Potentially they're
radio.
all far away from things and from each other.
Yeah.
Well, they might be connected through the house wiring. Okay, so what do you now have? Safety ground is great, right? You've got a great safety ground, no problem. But what do you also have in all of these grounds?
well, you're having to rely on the ground to create the circuit.
That's right. And in fact, depending on how you do it, you might also have your tuner grounded through the return line on the cable like this. And now what do you have?
Ground loop.
You have a loop. That's right. So where is actually 0 volts RF? No, I don't know. And the thing is, nobody really knows. This is known as a ground loop. And the problem with ground loops is that you can have current circulating, even though you think you're grounded somewhere, you can have RF current circulating in these wires. What happens to energy that gets to a point where it can circulate in a wire? That acts as an antenna. Current that's circulating in a wire also gets radiated because it's acting as an antenna, and you can have all kinds of problems. So what you do for that is you try to avoid ground loops as best as you can. So that means that your grounds, you want to basically look like this. Here's your main ground. And what it means is you don't give anything the ability to form a loop. You connect all your grounds to one point, and then that goes to ground. You avoid loops.
Well, that gets interesting in terms of what you're going to do in a house to an outdoor antenna, doesn't it?
Doesn't it though? Yeah, I know. That's why grounding is another one of those black arts.
Potentially a hell of a lot of wire and grounding. I mean,
Yeah. Well, ideally, you want as little grounding as possible.
Right. So I'm going to take my three instruments, what, computer, transmitter, and any other device, and try to put them, close it together on this, and then link to the larger ground for the antenna.
Yep. Because we're really talking about chassis ground. You know, you're talking about the frame of the thing. Now, the other question, of course, is, well, what happens if I have a grounded plug, right? And the grounded plug goes to ground. You do the best you can.
Well, that might be the ground loop right there.
Right, but you just do the best you can. You know, I would never recommend disconnecting a ground. You just do the best you can and hope that it doesn't cause a problem.
If
Since
radio's
we're
grounded to the house, that doesn't deal with RF, but would deal with the voltage.
Yeah. So what is a symptom of a ground loop? You receive reports of hum on your station's transmitted signal. Basically, you have RF feedback getting into things in your station. Um, what effect can be caused by a resonant ground connection? We talked about this. You can have high RF voltages on the enclosure of the equipment. I zapped my lip doing exactly that. What might be the problem if you receive an RF burn when touching your equipment when transmitting on the HF band? The ground wire has high impedance on that frequency. Well, that's exactly what we talked about. You basically have a potentially resonant ground line, which is the right length so that you now have a high voltage point right on your transmitter. And the thing is, if you change frequencies, that ground wire is no longer resonant. So it might not give you a shock on a different frequency. And in fact, it probably won't. But you will get a shock on one frequency, which is the unlucky one. Why must the metal enclosure of every item of station equipment be grounded? It ensures that hazardous voltages can't appear on the chassis. Basically, that's a safety ground thing. What technique helps to minimize RF hotspots in an amateur station? You bond all your equipment enclosures together. And again, bonding requires using as short a wire as possible and using typically a flat strap to keep your impedance as low as possible. Which of the following can be a cause of interference covering a wide range of frequencies? If we think about it, what is the RF componentry in lightning? What frequencies are in lightning? It's all frequencies. Lightning is broadband RF noise when it emits energy. It's a pulse and it generates noise, which is why FM radio is unaffected by it, but AM is really, really hampered by it. Well, a spark caused by arcing, caused by a loose connection, does the exact same thing, just on a much smaller scale. So if you have a poor electrical connection that causes arcing, an arc is basically a little lightning strike, you basically then have wideband RF noise. So you listen for that. Which of the following is an advantage of a receiver DSP IF filter as opposed to analog filters? This is the same reason that we use software-defined radios. We basically can take our filter and we can shape it using software. And because it's software and not hardware, we can change it. And since we can change it, it's not fixed. We want to make it something different. You can make it something different. All right, speech processors, S meters, sideband operation near band edges. Okay, this is how to use the radio. What's the purpose of a speech processor in a modern transceiver? A speech processor is kind of like, does everyone remember Dolby sound?
Yeah.
Right? Dolby is basically a way to enhance certain frequencies and make your audio sound better. Essentially, a speech processor is a voice enhancer that boosts certain frequencies and compresses others to make your signal have more punch. Now, if it's turned up too high, you can actually get distortion. But the overall effect is that if the conditions are lousy, you increase the punch of your audio, your signal will get through better. It increases average power and it increases the peaks.
Like an audio equalizer.
Yeah, except that your equalization is intentionally unequalizing it,
right,
to enhance certain frequencies that you want to get through.
To bring in what you want to hear.
Yeah. So if you think about it, I mean, human speech is typically between a few hundred hertz and 3,000 hertz. Right? 3,000 hertz is actually a really high pitch. Most of what we do is fairly low. Now, this is the same reason why my daughter, who's W7JI, who has her extra class license, whenever I can't get through to somebody, I say, hey, Hannah, you give it a try. And it usually works because different frequency range, it punches through better. What happens if your speech processor is turned on or turned too high? You can pick up background noise in your room. You can splatter all over the place, or your signal can be distorted to the point where nobody can actually understand you. Unfortunately, I've had that happen. We run a 10-meter net every Sunday night here. And if I leave the speech processor on from a voice contest that I was doing, people will say, you sound different. You sound kind of weird. And I turn the processor off. It's like, oh, it's okay now. So, what is used for casual discussion is not the same thing that's used for trying to get through heavy noise.
But on my Yasu, I've got a clear RX and a clear TX, which I assume is cleaning up the transmitter and receiving signal.
Actually, that's a CLR, that's a clarifier.
Clarify.
That which is something we're getting to. That's receiver incremental tuning. That's basically for operating split. Where is an S meter found? An S meter is found in a receiver. The S units, one S unit is approximately 6 dB of received power. So when they say you're S5, that basically means you're showing up as an S5 on the signal meter. Most meters are calibrated so that S9 is 50 microvolts appearing at the antenna port into a 50 ohm load. So every 6 dB less than that is one S unit. S meter measures received signal strength and how much must the power output be raised to change the S meter reading from an S8 to an S9. And 6 dB is 3 and 3. 3 dB is doubling. So 6 dB is quadrupling. So to go from S8 to S9 is a 4 times power gain. So what does that really mean? If you go from S7 to S9, that's an 8 times power gain. That's essentially the equivalent of somebody taking their transmitter and shifting it from 10 watts to 80 watts. It takes 8 times as much power to make it, but it's a 2 S unit gain. The question is that really necessary? Sometimes it is if you're at S0 or below and you go up to S2. If you're S7 and you want to go to S9, you probably don't need to do that. That's why the concept of buying a power amplifier is always a difficult one, especially unless you're really serious. If you go from 100 watts to 1,000 watts, what you've done is you've increased your signal strength by 2 S units across the board. But in generating 1,000 watts, you might actually have to install a 220 volt circuit, which means that you had to rewire your shack. So, some people want to do it. A lot of people don't for that very reason. How does a signal that reads 20 dB over S9 compare to an S9 signal? 20 dB is 10 plus 10 decibels. Every time you go up by a factor of 10 dB, it's how many times? 10 times. So 10 times 10 is 100. So 20 dB over is 100 times stronger. Okay, so operating on the edges of the band. Why should you never, let's say you're on lower sideband. Okay, so let's say we're on lower sideband and on 40 meters, we can go down to 7.125. Why should you never put your frequency below 7.128 megahertz?
Might bleed over.
It might bleed over because you're on lower sideband and your signal is 3 kilohertz wide if it's tuned properly, which means that if you're at 7.128, the lower edge of your signal will be at 7.125. If I moved it down by 1 kilohertz, then my signal would now be down here and I would be out of band. This is not as egregious as if you were, for instance, on upper sideband on 14.350 and you tuned your radio to 14.348 and your signal was up here. Why is one worse than the other?
No answer.
This is why it's important to study those frequency charts.
Because it's
And-
fallen off at the upper end, right?
Well, here's the 7.125 to 7.128. Our band goes from 7 to 7.3. So technically, we're still at least in a ham band. What's the upper edge of the 20-meter band? The upper edge of the 20-meter band is 14.350. This is actually going to be really important for you because as a general, you're going to have access to these bands. Well, 14.350, what happens if you're now outside of band? You know, basically, if you were on 40 meters and you're outside of the band plan, that's not as egregious as being outside of the band altogether. You are now outside of the ham band completely. Your signal is outside of the ham band, and that is actually instead of just kind of like, you know, violating a gentleman's agreement and a band plan, that's actually violating the law right there. Okay, HF mobile installations, emergency battery powered operation. And we'll take a break in just a couple minutes. Which of the following, let's see, which of the following direct fuse power connections would be the best for a 100 watt HF mobile install? You typically want to go straight to the battery using a heavy gauge wire. And why don't you want to use they call it the auxiliary power socket. When I grew up, that was called the cigarette lighter. Why don't you want to use a cigarette lighter to run a 100-watt radio?
Too small a wire.
Too small of a wire. The cigarette lighter is typically only good for about 5 amps. At 12 volts, 5 amps, that's 60 watts roughly, right? And that's 60 watts input power. The transmitter that you're using is typically going to be about 50% efficient, which means that this actually is good for about a 30-watt transmitter. So that's good for about a 30-watt transmitter. And in fact, I've used a 25-watt transmitter off my cigarette lighter with no problem. But I wouldn't run a 100-watt radio off of it.
Yeah. Now, some of the newer vehicles do have the access port
They
for
do.
higher amperage, but you should check the fuse on that one.
That's very true, because you don't want to blow the fuse.
Right.
Which of the following can receive radio interference? Which of the following can receive interference in a radio installed in a vehicle? Somebody have a cat?
Not mine. She'd be on my shoulder if it was mine.
Battery charging system can cause interference. The fuel delivery system can make a little bit of a whining sound, or the vehicle control computer can also make noise. What limits? Which of the following most limits which of the following most limits the functionality of an HF mobile installation?
I thought it was going to be your antenna.
It's the antenna, and you can work really hard and have a very functional system. I had a 1995 Dodge Neon where I had right behind the trunk, I had my screwdriver antenna and an 8-foot whip on it. And I went all out and I installed ground braids between the hood and the frame up here, and a ground braid between the trunk and the frame. And I went underneath the car, and here's the exhaust system, and I grounded the exhaust system, and I grounded the straps holding the antenna to the frame. And I mean, I went so far as to actually grind off the paint. I did the same thing up here. So basically what I did was I said, I'm not going to trust the welding job that was done to make sure that, you know, I have a good RF path. I made my own RF path, and I made, you know, thousands of contacts with that system. I said hundreds yesterday. It was really thousands. I had a lot of success with it, but a lot of it depends on, you know, what you're going to do. Your antenna system is absolutely the limiting factor in what you're doing.
And that's kind of a sad misconception. Most people think that the ground of the vehicle is really good, but the factory usually puts a lot of epoxy underneath things and totally isolates it.
Yeah. And
Which band were you operating on?
I did a little on 80, but basically 40 meters and up. All bands, all modes. And I used to drive a lot. So
Going back to the previous question where it said what can cause noise, why isn't the alternator in there?
that's part of the battery system, battery charging system.
Okay.
Charging
Oh yeah,
systems.
the alternator. I actually, on that car, I actually bought ignition noise suppressing wires. I bought a whole separate suppressor wire set for my ignition system.
Yeah, that's common nowadays. Most cars already have that.
Oh, but this was actually above and beyond the normal ones.
Oh,
it
kind of
was-
like my Ranchero.
Yeah, it was specifically going out and buying a set that was designed. It was $100
Yeah.
30 years ago for a set of spark plug wires, but they work so well. I actually tried to make my own. I actually took aluminum foil and wrapped it around my plug wires. You know what happened?
Yeah, yeah.
Can you guess what happened?
You weren't hanging on to it when you started, did you?
Well, basically the engine ran like crap.
Yeah, round it out, and plus you'll get shocked.
Yeah. But well, I learned then that adding capacitance to spark plug wires doesn't work real well. So, okay. What happened? What's one advantage or one disadvantage of using a short mobile antenna as opposed to a full size antenna? Your operating bandwidth when you're tuned is really, really low. It's very, very tight. So your operating bandwidth is very limited. The purpose of putting a capacitance hat on a mobile antenna. Has anyone ever seen a Texas bug catcher?
Yeah.
Okay, this is a Texas bug catcher. All right, so it's called a Texas bug catcher because it's an open coil and catches lots of bugs in it. The thing on top is called a capacitance hat. That basically allows you to lengthen your antenna the same way that adding a coil does, except that what's nice is that it puts it at the end of the antenna at where the voltage is high. So a capacitance hat lengthens a short antenna with the purpose of a corona ball up here, because you can get some very high voltages. If you install a corona ball, you basically allow more surface area for high voltage to exist and dissipate energy to the atmosphere. Without that, you can actually get arcing off the top. In fact, even with a corona ball, you can get arcing. So reduce RF voltage discharge from the tip of the antenna while transmitting. What's the name of the process by which sunlight is changed into electricity? That's called photovoltaic conversion. Thank you, Einstein. The approximate open circuit voltage from a fully illuminated silicon photovoltaic cell or solar cell is about 0.5 volt. What's the reason that a series diode is connected between a solar panel and a storage battery? And that is so that when the solar panel is off, like it's nighttime, you don't backfeed power through the panel. And finally, what's the disadvantage of using wind as the primary source of power in an emergency station? You can't control the wind, and therefore you have to put in a big battery system to store energy, which is okay. The batteries are getting more efficient, so it's not a bad idea to do so. All right, we're up to operating procedures. Let's take another 5-minute break, everybody.
Kenneth Moss, are you asleep? Okay, who's sleeping out there? Is it John or Kenneth?
That is a good question.
Not me.
Sounds like my wife at about 2:30 in the morning.
You know, my wife told me that I actually even still snore a little with a CPAP on. I mean, that's skill, right? All right, everybody ready to go again?
Let's go.
Let's go. Okay,
Let's go.
let me just reconnect my laptop. Four, four, 1, 7, 3, 6. I don't know why my laptop got disconnected, although I guess I kind of do.
Here's my wife's term for it, gremlins.
Yeah, no, well, I have an old laptop. And
Old gremlins.
yeah,
It's like
Okay.
people ask her all the time, why did this happen? And she says, I have no idea, but I'll fix it.
yeah. Okay, let's see. All right. Continuing right along. Do we have any questions before we get going?
Not here.
Okay. Okay, we are on to operating procedures. So that's phone, USB, procedural signals, breaking into a contact, Vox operation, which I really hate. What mode of communication is most commonly used on HF? That would be single sideband. The advantage of single sideband is that upper and lower sideband, as they're generated, carry the exact same information. So you only need to transmit one. In addition, in AM, the carrier contains no information at all. So if we can re-inject a carrier as a reference frequency in our receiver, we don't need to waste the power to transmit one. So it's very efficient. And also requires very less bandwidth. Again, AM is about 6 kilohertz. Single sideband is about 3 kilohertz.
Notice on the band chart, they want us to use upper sideband quite a bit.
They do. The break point is at roughly 10 megahertz by convention. And I think a lot of this came from what was easier to generate way back in the day. Anything below 10 megahertz is typically lower sideband, and anything above is typically upper sideband. In addition, most digital communications uses upper sideband, and any bands that have been added, like the military typically uses upper sideband, even on the 60, even in our case, on the shared 60-meter band. So it's mostly upper sideband. You have noticed correctly. So on 14 megahertz and up, we use upper sideband. If we're on the 17-meter band or the 12-meter band, we use upper sideband. If we're on VHF or UHF, you typically use upper sideband. If you're on 160, 75, and 40 meters, because those are below 10 megahertz, those are below the line, you would typically use lower sideband. However, it is not required that you use any one particular sideband, but if you use something that other people aren't expecting, they might say, huh? And then realize, oh, they're on the other sideband. So it's good amateur practice to follow the rules that everybody else is following and use the same sideband. So if I am calling CQDX, DX, if I'm in the United States, typically stands for outside of the lower 48. If you want to break into a phone contact, either using upper sideband or FM or whatever, you typically just throw out your call sign. And if somebody could hear you, they'll typically answer and just say, hey, I heard a call. Who was that? Or they'll give your call sign back. That's how you would break into a conversation. What control is typically adjusted for proper ALC setting on an amateur SSB transceiver? This is for voice and for digital. You have ALC, which is automatic level control. That determines whether or not you're going to splatter when you're transmitting voice. So you have an audio gain or transmit gain or microphone gain that allows you to set that level so that you don't make too much ALC action occur. ALC is a little meter that you'll see. Every single sideband transceiver has an ALC meter. When you're transmitting, you should see a little bit of ALC action, but not like, full, not like going full bore. The advantage and disadvantage of voice operated transmit, or VOX, is that VOX is great because you don't need to use your hands. If you're using a VOX headset, it also means that if you're driving your car and somebody cuts you off and you start yelling at them and forget where you are, you'll be transmitting that over the air. Therefore, I generally hate VOX because VOX is great, but VOX can get you into a lot of trouble.
It's also really bad if you're on a motorcycle.
Yeah.
Yeah.
Okay, now we're
Am I
on to Morse
appreciating that
code.
Vox automatically puts out your call sign just by
Nope.
hitting the switch?
No, Vox basically, whenever it hears anything, it keys the microphone.
Oh, okay.
It keys the transmitter, which means that if you're, for instance, like you get cut off and you have the Vox headset turned on and you're listening and you turn over and say, holy bleeping, bleeping, bleep, you bleeping, bleeping, bleep, you just transmit it over the air.
So VOX, voice transmission, X transmission. Yeah. Okay, got it.
Okay, now we're on to Morse code. How do you listen? What do you say when you want to know if a frequency is free? You want to know if a frequency is available. In voice, you'd say, is the frequency in use? In Morse code, we use Q signals for those things. My Q signal for is the frequency in use is QRL with a question mark. The answer to that is if the frequency is in use, somebody will say QRL. So all these Q signals, they could be a question and an answer. So for instance, if I were to say QSL question mark, which means, do you understand? Do you copy? The answer is QSL. Yes, I do. So,
Two meanings in one.
yep, one is a question mark.
One is a
and
question.
One is a question and one is an answer. Let's see. Which of the following complies with good amateur practice when choosing a frequency on which to initiate a call? You follow the band plan, make sure it's a ham band, where you're transmitting, and make sure you've got privileges to use it. Within the voluntary band plan, what is on 6 meters? Let's see. What is the voluntary band plan restriction for U.S. stations transmitting within the 48 contiguous states on 50.1 to 50.125? Is that right? That should be 50.125. So what we're going to do is we're going to share right here. Going to look at the 6 meter band and notice this thing called a DX window that says 50.110. Everybody see that on the 6 meter band? The DX window basically means, by convention, you stay out of the DX window unless you're talking DX being long distance. And in fact, the 6 meter DX window is 50.100 to 50.125. And typically every one of those VHF, UHF bands is going to have something called a DX window. The big one, however, is on 6 meters because you do get intercontinental communications on 6 meters from time to time. So let's see. When selecting an SSB transmitting frequency, what minimum separation should be used? Everybody remember, what is the approximate bandwidth of single sideband?
3 megahertz
3 kilohertz,
or kilohertz, excuse me.
right? 3 kilohertz. So how far apart should stations try to be?
3.
3 kilohertz. Yep, to avoid interfering. When selecting a CW transmitting frequency, this is why CW can be more effective as far as packing a band with signals. What's the minimum separation that should be used to avoid adjacent interference? Typically, a CW signal is about 150 hertz wide. So at minimum, you'd want 150 hertz. A lot of people will use a 500 hertz CW filter when they're listening. So you want to stay at least 150 hertz apart, ideally 500 hertz. So the answer is 150 to 500 hertz. What's good amateur practice? If propagation changes during a contact and you find yourself on the same frequency as someone else that you're interfering with. Well,
All
it happens all the time, actually. And what you do is you say, hey, let's move up 5 or down 5. Or you ask them, can you move up 5? Because you weren't, it's not like anybody interfered with anyone else on purpose. It just sort of happened because propagation changed. Nobody owns a frequency, period, except during emergencies. If there's an emergency, there may be a declaration that says that 14.275 is being used as hurricane watch or hurricane traffic frequency. If there's an emergency.
Does that come over the radio to let you know or something? Or
usually that'll come out as a bulletin from the ARRL.
Huh.
But if you accidentally,
and from FEMA.
yeah, if you accidentally get into it, someone will politely let you know. Hopefully.
Somebody will tell you.
Okay.
When is an amateur station allowed to use any means at its disposal to assist another station in distress? If there's an actual emergency, you can do anything you need to do. That means you can hop on a fire band, fire department frequencies, police frequencies. You might have some explaining to do afterwards, explaining why you were out of band and explaining why you were using frequencies that weren't allocated to you. But if there was an actual emergency that you couldn't solve in any other way, do whatever you need to do. What frequency should be used to send a distress call? That would be whatever frequency has the best chance of getting the message out. And it might be that, if that's like a search and rescue repeater up in the mountains and there's not a ham repeater nearby, or that you just heard somebody talking on the search and rescue frequency and you haven't heard anybody on the ham repeater for half an hour, that's probably justifiable. Get the message out. What's the first thing you should do if you're communicating with another station and hear a station in distress break in? You basically acknowledge the station in distress and determine what's needed, even if it means that they're not hams. Let's say that they heard you on a ham radio that belonged to somebody who got injured. They grabbed the radio and they're talking to you. Well, you know what? It's an emergency. They're allowed to do what they need to do, and you should help.
God, has that ever happened to you in your years?
It has not. Although I've been able to provide assistance to somebody who was driving a truck and got turned down a street where they couldn't make a turn and couldn't make a U-turn. Was able to sort of help them out that way. I was listening to one of the local repeaters where somebody had broken their leg. It wasn't a ham, but there was a ham nearby and there was no cell phone coverage. And they called out on a repeater and they basically said, okay, this repeater is now exclusively for the use of this emergency thing. And they kept it exclusive for an hour until the EMS got there and they hauled the person off to the hospital. Who can be the control operator of an amateur station transmitting in RACES? RACES is the Radio Amateur Civil Emergency Service. To assist relief during relief operations during a disaster. Basically, if you're a RACES operator, you still need to be a ham. You have to have a ham license to operate as part of RACES. Okay, so more Morse code stuff. What What is the best speed to use when answering a CQ? It is very likely that the person who is transmitting at a speed that is comfortable to them, which is probably about the same speed that they are comfortable receiving. So whatever the speed is coming in, you should answer at the same speed. Unless of course you want to go slower, you can always go slower.
Yeah, if you can't go that speed, would just explain that, this is the speed that I'm comfortable with, or?
Yeah, you just answer at a comfortable speed for you,
Okay,
so long as it doesn't exceed the other one.
right.
And like I've actually like called CQ at like 30 words a minute and I'll get an answer at 15. Ideally, my response to that would be I would slow myself down to 15 because obviously the other station is calling me at 15 because that's what they're comfortable doing.
Okay.
What does it mean to zero beat in CW? Zero beating means that you're basically matching your transmit frequency exactly to the receive frequency. When sending CW, if you add, okay, RST, there's something called RS, which is readability and signal. In Morse code, we add a T, which is tone. If somebody is 5 by 9, that is a common signal report. That is readability and signal. That's 1 to 5 and 1 to 9. And tone is also 1 to 9. So a perfect report is 599 in Morse code, and it's 59 in voice.
What does read you 5 by 5 in this case?
Well, I've never given anyone a 555. I've given you'll tip. It's very uncommon for somebody to have a lousy tone, although I have given somebody less than a 9. A 579 typically will pull this off the signal off the S meter. You could be a 319, in which case you're barely audible. I've had a couple of contacts this weekend that were like that. C at the end indicates a chirp sound. So you hear that a lot during field day when stations are operating off of batteries. And when they're operating off of batteries, if the battery voltage is getting low, when they key up, the battery voltage drops even further. And that can sometimes make the transmitter frequency unstable. And that can add a chirpy sound. You indicate that with a letter C. Okay, QRS. Now we're into our Q signals, of which there are hundreds and hundreds. We don't really need to know that many. QRS means slow down. It can be asked as a question, or it can also be stated as, yes, I will slow down. So that's QRS, which means slow down. Anyone know what QSL is?
Question or an answer.
QSL is a confirmation. Do you confirm something? And the answer is QSL. Yes, I do. Oops. Or I acknowledge receipt. It's quite literally. QRN versus QRM. Those are both types of noise. QRM is man-made. QRN is natural. So QRM would be static from a nearby station, a splatter or something. QRN would be lightning, static crashes. QRV means I am active and ready to receive. Okay, so if I were to send CQ means I'm looking for somebody to talk to. If I'm doing it in Morse code, I would send CQ, DE, N7JI. By the way, I also teach Morse code. KN. I would not do a KN in this case. I would do a K. The letter K means I'm looking for any station to reply. So if I were to instead, let's say, get called by KJ7ZTW, and my reply was KJ7ZTW DE, DE means from N7JI KN. That would mean I'm not looking for, like the K, anyone to reply. I'm specifically looking for Ray, who I referenced right here, to call. That's what the symbol KN means. and that's known as a pro sign. It's a spelled PROSIGN, and it's a procedural signal. So that's known as a
Designated to
pro
one
sign.
person.
So that's known as a pro sign. So KN, interestingly, KN as a pro sign is sent all mashed together. So K would be da da da, N is dotted. When you're sending KN, you would actually write it like this, and it would be da 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 da. You mash the signals all together. If you're ending a message, you send da 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 da, which is AR as a pro sign. Okay, full break-in telegraphy. Okay, when you're transmitting in voice, typically you can't hear what's happening on the other side, right? It's one-way communications at a time. If you're using break-in, that basically means that when you key your Morse code key, you're switching your transmitter into transmit, and then when you let go, there's a delay. If you're doing something called QSK, which is break-in, and in particular full QSK, that means that you are, let's say you transmit individual letters or let's say dits and das, that in between, let's say a dit, da, depending on how it's set, your receiver actually operates so fast that you're actually able to hear what's happening in between the characters that you're sending. And that's known as full QSK or full break-in. What's nice about that is that you can hear if somebody else is trying to break in to your conversation while you're transmitting. That's why it's known as full break-in. Okay, volunteer monitoring program. The volunteer monitoring program is amateur volunteers who are formally enlisted to monitor the airwaves for rules violations. So it is a general rule that we do not want the FCC involved in our business. The FCC regulates us, they give us our licenses, but they handle egregious things. But for the most part, we don't give them a whole lot of money, and they don't want to spend a whole lot of money on us. They don't want to think about us. They don't want to look at us. They want us to be dealing with, issues ourselves. So they basically say, make this volunteer monitoring program and handle it yourselves before anything gets to us.
Play nicely, children.
Yep.
Yeah, volunteer
'Cause-
monitoring.
Yeah. So, and which of the following are, what's an objective of volunteer monitoring program? To encourage amateur operators to self-regulate and comply with the rules. Because in this particular case, it's a lot better to know the rules and to know the rules and do the right thing than it is to have somebody tell you what to not do.
So we might get one of these monitors contacting us after a violation, either
Yep.
by.
And it's a lot better. Well, and actually I've known lots of people who were part of the monitoring program in one form or another. They said that they would typically send out 19 attaboys to every one violation.
Oh, when you do right, you get a message?
They'll send you a message saying, hey, you were heard and good job. You're setting a good example.
Da-dee-da-dee-da.
Yeah. Most of the violations that you'll hear, believe it or not, that don't require any kind of FCC involvement, sometimes you'll get people who are just intentionally interfering with each other. That's an FCC thing, right? But a lot of them are like, somebody's too close to the band edge. They don't realize that a little bit of their signal is hanging out, especially during a contest. They're kind of like focused on making the contact and not really noticing that they're just a little too close. So you might get a letter for that. But again, that's something, it's fixable. Just be aware of it.
Yeah, that's like one net we had. I don't know if you were involved, that someone bought a $20 Baofeng, I think, and happened to hear it and started playing the radio.
Really?
And it just went on. Oh yeah. Yeah. That was, I think that was on the Now What on Monday. Yeah. Just playing the radio over it, but everybody else was strong enough we could talk over it. And
Yeah,
we just kind of ignored it and hoped it'd go away.
that's the right thing to do. All right, let's see. What skills learned during hidden transmitter hunts or have helped to the volunteer monitoring program? Well, part of the volunteering monitoring program is being able to find the hidden transmitter. There was actually very recently somebody who was, or something that was transmitting on about 7.030 megahertz. And it took several days to find it. And what it was a malfunctioning, this is in a ham band, a malfunctioning remotely controlled transmitter at somebody's vacation house.
Huh.
And enough people were able to track it down. I mean, and it was in like Utah, in like Zion National, around Zion or something. It's not near anything in particular. And they were actually able to figure out what general direction it was. And they got closer and closer and closer and finally figured out, oh, it's coming from this square mile. Do we have any hams there? And they contacted him and he said, oh, crap. But they found it, it wasn't like it was on purpose. It was just something that was malfunctioning. So direction finding. Which of the following describes an azimuthal projection? Okay, azimuth is the angle from 0 to 360 degrees on the horizon, basically, or looking down at the earth. So if we were to look at an azimuthal projection taken from where I live, I'm going to pull one of those up. I think I have that here. Look at that. This is an azimuthal projection taken from Western Oregon, where basically you have your heading to get to a certain place. And you also have each circle is 3,000 miles in length. So you see the 3,000 mile circles, the inner circle, then there's the 6,000 mile circle, the 9,000 and the 12,000. The heading tells you which direction you go to get there. So that's an azimuthal projection. And if anybody would like an azimuthal projection, you can notice it says courtesy of N7JI. You can go to his website, look him up, plug in where you live, and it'll generate one for you for free. How is a directional antenna pointed when making a long path contact with another station? Well, let's take a look at that map again. So let's say that I want to make a contact into Europe. Okay, so into Europe, it looks like my beam heading from here is, depending on where I'm going, about 30 degrees. If I wanted to go the long way, then I would have to come up the other way, which means I'd have to go 180 degrees off of that. So I'd have to aim at 210. So I'd have to aim south-southwest, and that would come up around the long path. Which of the following is typical of the lower HF frequencies during the summer? Typically, if you think about, does anybody here live in the Southeast? You ever have any thunderstorms down there?
All the time.
All the time. Okay, so there are a lot of thunderstorms. Now, you wouldn't think that the thunderstorms in South Carolina have much impact on Oregon, right?
You would think.
You would think, but you know what? They do. And in fact, because radio waves travel really long distances at night, thunderstorms all over the world create RF energy that travels all over the world. So basically, if you listen to 80 meters or 160 meters during the winter time, when you have, might have some thunderstorms in the southern hemisphere, they don't usually impact us too much. But during the summer in the northern hemisphere, when the conditions should be okay for operating on those bands, we get all that low energy, all that very low frequency RF energy that's being generated, and it echoes around, and all you hear is crash, static, boom, crash, crash, over and over and over and over. And it makes the bands almost completely unusable. So lots of static crashes. What's a good way to indicate on a clear frequency that you are looking for a contact with any station? CQ, CQ, CQ. And then you give your call sign. This is November 7, Juliet, India, N7JI. November 7, Juliet, India. So CQ a few times. Now, I've often heard people say CQ, 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 CQ. What's the
Oh,
problem
boy.
with that?
Nobody
Fail
gets
to give your call sign.
Yeah, everybody gets bored and listening and they
Yeah.
tune somewhere else. So, yeah. So, and eventually they'll give their call sign, but yeah.
Gotta unkey the mic before you can give your call sign.
That's right. But if you never call CQ, then people don't
Yeah.
know you're there. So
Right.
The way it was written, it sounded like you're required to give your ID, like up front, right after
Nope.
the first couple CQs, but
Nope.
not.
you don't have to give your ID until 10 minutes.
Wow.
You don't have to ID. You have to ID after every 10 minutes and at the end. There's no requirement of giving your call sign at the beginning.
Okay.
Okay, let's see. Now, why would I give my call sign as November 7, Juliet, India versus N7JI?
Clarity.
Yep.
Not clear to understand.
Phonetics, Alpha, Bravo, Charlie, Delta. That's actually on the test. The reason to give phonetics is for clarity, especially during lousy conditions.
I've noticed on some people will use their own little personal phonetics on that. It's just, I know it's not required to give it, guess I'm trying to get tongue tied here, but they'll use their own little variation of, instead of Zulu, they'll use, like
Zanzibar.
one gentleman used Zanzibar. Yeah.
Right.
Okay.
Or
I'll-
substituting police.
Yeah, well,
Mary
and
Edwards.
I'll sometimes in a contest, I'll give November 7, Japan, India, or Japan, Italy. Just because, if I've tried 6 times and they haven't heard me yet, I'm going to change a little bit and see if I can't, be heard better. If I'm trying to get heard in Japan, I'm going to give Japan because they're used to that. So, when operating in a contest on HF frequencies, you still have to identify your station by normal FCC regs. QRP, that's another Q signal. QRS means slow down. QRQ means speed up. QRP means low power. Or do you want to reduce your power? QRP is an entire movement, basically, which is low power operation. Typically in the United States and most of the world, it refers to 5 watts of output power. Why do many amateurs keep a station log? You don't have to, but in case the FCC looks for help, you'll have a log handy. Now, personally, I like to have a station log because I like to keep track of a lot of the contacts I make. I don't keep track of most of the FM repeater contacts I make, hardly any for that matter. And I've got, close to 30,000 contacts that I've made that are actually logged in Logbook of the World. If I were to add all of the 2-meter and FM repeater contacts that I've made, it would probably be closer to 50 or 60,000. Okay, digital subbands. What section of the 20-meter band is most often used for digital transmissions? That would be 14.070 to 14.112. There's no real way to memorize that other than to memorize it. In what segment of the 20-meter band are most PSK31 operations usually found? And that would be below the RTTY segment and now below the FT8 segment. I think in this case, it's going to make a lot of sense to just draw this out. 14.070, 14.112. Okay, 0.074 to 0.077 or so. This is FT8. And this entire band is really RTTY. And right here is PSK31. And up here, I think at 0.085, this is FT4. And as more modes are created, there's stuff shifting around all the time. So, as soon as they made these questions, I'm sure that it has actually changed.
What's the point of having you memorize this arcane stuff here versus actual things that will make a difference?
Well, you at least need to know that it's there, like FT8 was, FT8 is 0.074. But sometimes there'll be a de-exposition that'll be at 0.090. And then there's something where they're operating called FT8 Fox and Hound, which is a different mode altogether. So the thing is, you have to have somewhere to start. And they only change the question pool every 4 years. So, we do the best we can.
It's called whatever.
Yeah. But it's a good place to start. What section of the 80-meter band is most commonly used for digital transmissions? This is still true. 3585 to 3600. It's not very much space. Digital typically doesn't take up much space. The most commonly used frequency shift for RTTY emissions in the amateur bands is 170 hertz. Again, it's radio teletype, RTTY. And this is a form of AFSK, which is an audio frequency shift keying. And in audio frequency shift keying, if it's two things, you have two signals. They're called mark and space. And in this particular case, they are at 2125 and 2295 hertz. And that is a frequency shift of 170 hertz. So there you go. That's what RTTY looks like. If you were to draw it, you'd basically have signals right here and signals right here, and they just basically bounce back and forth. If you're looking at it on a waterfall chart, it basically looks like a pair of train tracks. Very easy to tell what RTTY looks like compared to anything else. What mode is normally used when sending RTTY via AFSK on an SSB transmitter? Lower sideband. And I will say that of late, because a lot of people have been using software to generate their teletype of late, a lot of people actually use upper sideband too. But the rule is, conventionally, you would use a lower sideband. And what happens if you switch from one sideband to the other, where you have, for instance, mark and space, and you switch from lower sideband to upper sideband, and you're trying to receive? Your space and mark get reversed.
And so it doesn't work.
It doesn't work, exactly. You'll basically just receive garbage on your screen. That's the way to know that you got it backwards. What is the standard sideband used to generate JT65, JT9, or FT8? The answer is upper sideband on any amateur band. Okay, so which of the following connectors would be a good choice for a serial data port? That's actually called a DE9. If you look it up, I did not know this. If you look it up, a serial port is actually known as a DE9. It has 1, 2, 3, 4, 5, and then 1, 2, 3, 4, and it looks like this. Everyone recognize that?
Yeah, it's just not used in computing anymore at all. Completely replaced by USBs.
We actually always called this a DB9, right? But actually, that's not the proper name for it. The proper name is a DE9 connector.
We're going to be
So there
slowed
you
down by baud rates on this.
Yeah.
I still use one on an old Garmin that I've got
Yeah, I mean,
adapted.
there's still hardware out there that has them.
Yeah.
I mean, I still do like Zebra printers. The Zebra printers have those.
Yeah.
Not anymore. They're USB now.
Well, they have become USB. I know, but that doesn't mean that I always have access.
I do
to
point
them.
of sale computers, and so yeah.
Takes forever for the information to get through sometimes. But
Yeah.
Ooh, yes. 9600 baud.
Yeah.
Don't help.
Yeah.
Okay, which of the following is a characteristic of FT8 of the FT8 mode of WSJTX? Okay, so here is an FT8 contact, CQ N7JI CN84. There's my grid square CN84. Okay. Here is the response. N7JI KJ7ZTW minus 12. KJ7ZTW and 7JI R minus 11.
So KT8 is just all text?
FT8. Yeah.
FT8, I'm sorry, is all
Yeah.
text?
Yep.
No voice. Okay.
Nope. That's a contact.
Wow.
That's what it looks like. So, and so like here, I gave my signal report, and or I gave my grid square, and depending on the contact, Ray may also give his grid square as well. But this is what it looks like. N7JI from KJ7ZTW, you're a minus 12 in CN84. KJ7ZTW, N7JI I received it, you're a minus 11. N7JI from KJ7ZTW, RR means I got it, 73. The response is, all right, 73. So that is, as they say, for some people, exciting. And for some people, it's the equivalent of watching paint
Yeah,
dry.
yeah.
Oh, Dolesville.
Yeah, it's the equivalent of watching paint dry. However, what is kind of interesting is that because there's so little information exchanged, a lot of Morse code contacts are very similar when you really think about it. It's a signal report and where you are, especially if it's a rare station. So
Very quick.
it's very, very quick. This whole thing takes about 1 minute, and it's really, really, really good because the data rate is so slow and there's so much error correction built in. And I mean, I could spend 15 minutes explaining what the actual modulation scheme is and why it's so ingenious.
Where's the list of codes for the responses and where you know what R11 and R73? I assume there are others.
Basically, you run the WSJT software, WSJTX, and those are canned messages.
Ah.
And so you don't, there's nothing freeform. It's all canned messages based on who you clicked on to talk to.
It's like analog selection.
Yeah. So the interesting thing about it is that it's great for really, really lousy signal conditions. And if you run very low power, it's great for that too. Like I'll make a lot of contacts from hotel rooms by this method. And you know, it's not as much fun as operating doing Morse code for me, or operating doing voice, or a lot of different things, but it does work. And if I happen to be in the middle of like writing or something, or doing something else like work, well, this takes almost none of my brain power to do. And I can still make contacts. So, but this is FT8. So one of the things about FT8, you exchange call signs, grid locators, and signal reports. That's about it.
Huh.
One of the things that's required of FT8 is because each of these is a 15-second period, and somebody transmits on the evens and somebody transmits on the odds. In the 15-second periods, you have to switch back and forth. Everybody has to be time synced to about 1 second. So your computer that's doing this needs to be time synchronized to about 1 second, or else it'll fall outside of the window.
Did you say yesterday that text can actually use FT8?
Do it on 10 meters.
So that was one of the things that was first available.
Yep.
Especially for low power situations, even if you don't have your antenna up.
Mm-hmm.
So only on the 10 meters.
Yep. Yeah. Right here. You see the blue hash, I believe. Right. Oh, right here. Right here where that red bar is, it says CW Iridium data.
KT8
So on
data.
10 meters, as a star, the star indicates novice and technician. So literally anybody, any licensee can use data on those bands, on that band. Notice that on 15 and 40 and 80, we have the green hash. Notice that says not literally novice technician CW. Even though other people can use data, you're only allowed to do CW there.
I see
And-
why they were telling me the 10-meter band on voice only now.
Yeah, that's wrong. You can do voice there. It's the only place you can do voice. Okay, let's see, where were we? Oh, let's say you're listening to RTTY or other FSK signal and you seem to have it tuned properly, but you can't receive it. So you got the wrong baud rate, you got the wrong band, you're on the wrong sideband, or your mark and space could be reversed, which is really the same thing as, selecting the wrong sideband. Okay, communication system uses the internet to transfer messages. That's known as WinLink. Does anyone here use WinLink yet?
Mm.
It's very, very big in emergency communications. Hey, Mike, since your hand went up, you got to describe it a little.
One of the nets here uses WinLink. So they tie a lot of repeaters throughout Ontario together and used primarily for doing foul weather forecasting.
Okay.
Is WinLink just texting or also allowing voice?
It's with voice.
And there's also sending data messages as well. I mean, you can do email over WinLink as well, right?
Yeah, I mean, it's used as accessing a net where you don't have access to the appropriate repeaters, but you can go in through WinLink through the internet and tie into a repeater that way. So, for example, I've seen sessions where we've had discussions on a net where the net control was in Toronto, and one of the guys joining the net was down in Rochester in New York.
Vicky and Jack Simmons.
So that be, it's similar to Echolink, but
Yes.
it's prioritized.
And it's also it's also not free. That's one of the other things.
Right. Okay. Because that's what I like about Echolink. You can get onto anybody there.
One of the things about WinLink is that there's an email system that's kind of built into it as well. Okay, let's see. Which communication system sometimes uses the internet to transfer messages? That's called WinLink. Which of the following is a way to establish contact with a digital messaging system gateway station? So you basically have a connect message. You publish the frequency will be published. You say connect to whatever the station is, and if it's there and it's active and ready to accept connections, you can connect to it. How can a Pactor modem or controller be used to determine if the channel is in use? You can put the modem or controller in a mode where it allows monitoring communications without making a connection. And Pactor is an interesting mode. Pactor and Winmore, if there are other stations interfering, you get frequent retries or timeouts, long pauses in message transmission, and failure to establish a connection. And let's say that you have station A and station B communicating over Pactor. How do you join in? And the answer is you don't. It's peer-to-peer, one person to one person. So there is no way to break into a communication link, but that's why you would try to monitor to see if a particular station is busy.
You have
All
to
right.
listen to it in a certain length of time. You can break into it.
Yeah, if there's nothing there, you can always
If
say,
there's
hey, I'd
nothing
like
there.
to connect.
Okay.
Okay, let's see. Next, RF and electrical safety. This is very similar to what we did on the technician license. One way that RF energy can affect human body tissue is that it heats the body tissue. So this is how microwave energy works. That can be used to cook things. We typically deal with considerably lower power levels and different frequencies than a microwave oven, but the end effect is the same. It doesn't have enough energy to generate any cellular damage on a DNA level, but it can cause heating of tissue. Time averaging, referring to radiation exposure, is the RF, the total RF exposure averaged over a certain period of time. Duty cycle, a lower transmitter duty cycle allows you to transmit for higher power, so you achieve the same average. So if I were allowed an average of 1 watt of 1 watt of energy, I could transmit 2 watts for half the time. I could transmit 10 watts for 1/10 of the time, and I'd still have the same average. When determining if an RF signal exceeds the maximum permissible exposure, you need to look at duty cycle, frequency, and the power density, because all of those things figure into whether or not something is safe. What precautions should you take if you're installing an indoor antenna? I know we've got some indoor antennas discussed. Make sure that the minimum permissible exposure limits are not exceeded in occupied areas. If you live in a townhouse, this includes the people who live next door to you who don't know that you're transmitting. The other thing is that you have to perform. Now you actually have to perform with any station an RF exposure test or limit RF exposure evaluation. So what I'm going to do is hopefully open up a browser. Here we go. And we're going to go to this website, power density. Okay, has anyone ever been to this site before?
No,
Okay, I'm going to put this out in the chat. And the reason I'm going to put this out in the chat is because this is an incredibly useful little website to have access to. You can actually go around and you can take you can use calibrated equipment to measure your field strength. You can do computer modeling, or what you can do is just very simply go to FCC OET Bulletin 65. Well, you can actually read that, or what you can do is go to this guy's website, which basically has an RF exposure calculator based on the FCC's bulletin. So I can say the average power at the antenna is 100 watts. Average power, I'm running a lot of power. The antenna gain, notice that it's in dBi. Does everyone remember what dBi is compared to dBd?
Isotropic.
Isotropic radiator. That's right. So notice I enter 2.2 for a dipole, or add 2.2 for any other antenna. So we're just going to use a dipole, 2.2. We're going to say in meters, we're 10 meters from the antenna, and we are at 14 megahertz, and go. So here's our power density in milliwatts per square centimeter. In a controlled environment, which means that I have access to, I'm saying that everyone in the area is aware of what's happening. That would be a controlled area. In an uncontrolled area, the limit would be 0.92 milliwatts per square centimeter. That means you don't have control of people walking by, or they're unaware of what's happening. Well, as it turns out, for 100 watts at a distance of 10 meters, which could be an antenna on a 30-foot tower, look at that, at 100 watts, even if you're transmitting 100% of the time and you have cable that doesn't lose any power, you're well within the safety limits. Okay, so then you take this, you enter performed on, and you enter by who did it, and you print it out and you put it up on the wall. That becomes your RF safety evaluation. Okay, what type of an instrument can be used to measure an RF field? That would be a calibrated field strength meter with a calibrated antenna, if you really wanted to do that. If you find that your station exceeds permissible limits of RF exposure, what do? You can put up a fence around your antenna. You can fence in your property. You can put up signs that say danger, RF exposure. That way then people know what's going on. You can also reduce the amount of time that you're transmitting. Reduce your power level, change the antenna. You just basically take whatever actions necessary to prevent human exposure to RF fields that are excessive. If a neighbor might receive more than the allowable limit of RF exposure in the main lobe of a directional antenna, that's why we do this. If you have an antenna that has 30 dB of gain and you point it at your neighbor's house, your neighbor is now receiving, let's say you're transmitting with a watt, your neighbor is now receiving the equivalent of 1,000 watts aimed right at their house because of that 30 dB antenna. So it's important to make sure that the neighbor's house cannot be in the target field, or you can put it up higher so that the neighbor's house doesn't get exposed. What precautions should you take whenever you adjust or repair an antenna? Turn it off, turn off the transmitter and disconnect the feed line so you don't get an RF burn up on the tower. If you're using a ground mounted antenna, make sure that nobody can get to the antenna. This is what typically happens when you have an AM radio station. You have a tower that is ground mounted, you put a fence around it and say danger, high RF energy, no trespassing. You can do that on your property too.
That's the problem that we had with POTA is people walking around and looking at and wanted to look right up at the antenna, and the person sending wasn't aware of it. And
Yeah.
all of a sudden, wow.
And that's when you put up caution tape that says,
Right.
you know, limited access.
Right.
So which of these choices should be observed when climbing a tower using a safety belt or harness? Make sure that the belt is rated for the weight of the climber and it's within its allowable service life. Don't use a worn out safety harness. What should be done by any person preparing to climb a tower that supports electrically powered devices? You make sure that the power supply is off and locked out and tagged. Good old lockout, tag out for those of us who work in industry.
Yep.
Why should soldered joints not be used with the wires that connect the base of a tower to the system of ground rods? Does anyone know this? Jim or Ray, I bet you know.
Yeah. Well, yeah. It just, I mean, it heats up. The solder can be tore apart, damaged.
If you get a lightning strike,
yeah, it'll melt it.
solder will melt. So CAD weld or mechanical connections.
Very, very low heat causes it to disappear.
Which of the following is a good practice for lightning protection grounds? They have to be bonded together with all other grounds. And now a little bit of electrical safety. National Electric Code governs electrical safety inside the ham shack, as well as industry and the house and mobile equipment and everything. According to NEC, the minimum wire size that can be used for a 20 amp circuit breaker is number 12.
Or higher.
Or bigger. Yeah, well, I said minimum.
Yeah.
Which, what size of fuse or circuit breaker would be appropriate to use with a circuit that uses number 14 wiring? That would be 15 amps. So 14 gauge is 15 amps, 12 gauge is 20 amps. Which wire or wires in a 4-conductor connection should be attached to fuses or circuit breakers operated from a 240 single phase source?
Two that carry the highest voltage.
Yep, you want to fuse the current carrying wires that are at voltage. So you fuse the wires that are carrying voltage.
That was a problem with the gentleman I worked with that didn't understand that.
Did he
And
fuse the
lost an
neutral?
arm. Yeah, he lost an arm when he grabbed the wrong ones and ground.
Ooh.
Yeah.
Which of the following conditions will cause a ground fault circuit interrupter to disconnect the 120 or 240? So a ground fault interrupter is one of those annoying things that can save your life. The way that a ground fault interrupter works is it has a differential measurement that says, okay, here's my current going in and here's my current going out. And I'm measuring the two. Well, if I look at my device and I look at the wall, there really should only be 2 wires that are carrying current. Well, if I sense that something in my double insulated hairdryer or something allowed a current leakage to somewhere, then my return current would not be equal to my ingoing current. And if I sense an imbalance of anything more than like 3 milliamps, I'm going to open up the circuit and protect the person who's being electrocuted. Now, one thing that's interesting is that I have in my life tripped many GFCIs by using ham radio. But by and large, it's still a very good thing to have.
Yeah, a lot of people will bypass those thinking that their item that it's tied to, is good or such, but they don't take it as a signal that, yeah, trust me, that's telling you something, especially people that have ponds and fish ponds and stuff like me.
Yeah.
They think, oh, the GFI has gone bad and it keeps tripping. Well, normally it's the pump's gone bad. It's leaking.
Right. So the idea, really, the thing to do is get a new GFCI, and if that doesn't fix it, so, all right, let's see. What's the purpose of a power supply interlock? That is to remove dangerous voltages from a cabinet when it's open. This is very common in a high voltage transmitter or an amplifier. Even the old Heathkit 220s, which had a pair of 3500Z power tubes operating at about 3000 volts plate voltage, if I remember right. They had a little switch inside, which if you opened the lid would turn off the power supply so that you didn't die. Every so often somebody wanted to do a test on it. And so what they did was they took a piece of tape and put it on the limit, put it on that interlock switch. And then they stuck their hand in and proceeded to electrocute themselves at 3000 volts and didn't live to talk about it. So don't do it. What must you do when powering your house from an emergency generator? You need to disconnect the incoming utility power feed. The reason being that we're going to talk about transformers a little bit, very, very quickly. So let's talk about our, let's talk about
the neighborhood power.
Right. Let's talk about our 12,000 volt to 120 volt step down transformer. Okay. So let's say you have a bunch of utility people who are working on the power lines after an outage, and you're like, oh man, I don't want to deal with having no power. So you basically take your 120 and you plug it into your generator so you can run your house, right? Well, if you are not disconnected from the utility system, this transformer works both directions. It works that way and it works that way. So your generator, in addition to running your refrigerator and your lights and things like that, it is also putting voltage into the transformer, which, because now it's operating as a 100-to-1 step up transformer, you are now energizing the power lines, which are supposed to be off because they're disconnected somewhere at 12,000 volts, which means that the guy who is operating and working on these power lines and trying to get power restored to your house just got killed. So very important, if you're going to be doing that, to have a disconnect so you can disconnect yourself from the power lines and run your house off of your temporary generator. Which of the following is true of an emergency generator installation? It should be in a well-ventilated area. Not just well-ventilated, but if this is your house and you have air intakes over here, don't put the generator right here. A primary reason for not placing a gasoline fuel generator inside an occupied area is that generators, along with any other gasoline powered equipment, will make carbon monoxide, which is odorless and tasteless and will cause you to die. Which of the following is a danger from tin lead solder? Lead can contaminate food if hands are not washed after handling. If you also happen to smoke, people who solder a lot and smoke can get a fair amount of lead from their fingers through their cigarettes. So make sure you wash your hands. And how about a 20-minute break for lunch?
Wow.
Is that good?
Sounds good.
All right.
Mo-
We're
motion
getting there.
carries.
We're getting there, everybody.
Fuck. Damn it. Shit. You kicked it. Fuck, I don't know what you expected to do. Damn it. Well, you're gonna have to repair that before we do anything else. So,
Now I know what my dad went through when he was building radios and TVs, Scott, when he was coming to the old stuff.
Yeah. Well, you follow schematics and sometimes things work and sometimes things don't.
Are you talking about heating things up? It's like he used to, I mean, I was just a kid, but I remember him putting a fan in the back of the TVs while he was working on them, trying to keep things cooled down until he could figure out what was going on. And keep telling me not to stick my fingers in there.
Don't stick your finger in there.
Yeah. Sad thing about that was I was so interested in it that he gave me a cord, and I don't even know what it went to, but basically the ends were cut off and they were stripped. Said, here, go play with this. Well, you give a kid something like that, and went in the house and hid behind the chair and plugged it in, and I've got the scars on my arm to prove it.
Do you really?
Yeah, they're almost gone, but yeah, I knocked out the entire cul-de-sac we were in, I guess. It shorted at the time. So yeah, I learned real quick about that.
Oh, let's see. Let's see where we are.
Commission rules?
Commission's rules. What I like about this part is that it's basically just memorization on this.
Yeah, like the first question that's the way I remembered it is the first three were in even numbers.
Yeah. Yeah.
60, 60, 30. And that's how
Oh, I like that.
Yeah. That's how I have to do a lot of these. They confuse me, but what I do is I look at the choices that you have, like in different frequencies, and then I find that the answer happens to be the one choice that has the numbers in it of either higher or lower.
Mm-hmm.
Scott, I have a question.
Yep.
I've scheduled my test for Tuesday.
Okay.
If I fail it, will they offer me a second chance to take it right away if I'm close or no?
Well, I mean, they're not obligated to, but it depends who's doing it, but most of them do. Yeah.
That was if I came close,
Yeah.
because the next time you take it, it's going to be a different pool, right?
This one doesn't change till 2023.
I meant not by the pool, but the.
It'll be a
exact
different group of
question.
questions.
Oh, yeah, it'll always be a different test. They're randomly generated.
And what was the one saying? You should always ask for the easy one.
Yeah, right. Just give me the easy test.
Just give me the easy test. That'll work for me.
Earlier audio is really weird. Does anybody else hear that?
Yep.
I do. It sounds like a child.
It does. It sounds like a cat.
The cat.
Sounds like either a cry or something distorted like a cry.
Yeah. That's very weird. Well, are we ready to get going again? I thought,
man.
no, not yet.
Get
Okay,
it
so
done.
now we're really done with all the hard stuff. Now it's memorizing and things like that. All right. Here we go. General class operator frequencies, privileges, et cetera, et cetera. All right. As Ray was saying, the answer to on which bands is a general class license holder granted all amateur privileges, 160, 60, 30, 17, 12, and 10. Now, for me, this actually is not that hard because I was around when the 30, 17, and 12 meter bands came into existence, or just afterwards. Those are the special bands. Those are not the classic ham bands. Neither is 60. And 160 and 10 were always for everyone. And 60, 30, 17, and 12 were created with access for general and higher because they're really small. So, but that's the answer. You just have to memorize it. Which of the following frequencies is within the general class portion of the 80 meter band? Well, you know, the only way to do this, let's take a look.
Where did you get that band plan at?
I sent this as part of the cheat sheet package to everybody.
Oh, I didn't get that. Sorry.
You didn't get that from me?
No.
It was,
You have to unzip the file.
yeah, it's part of a big zip file.
Oh, yeah. Well, me and computers don't get along. I'll have the Wi-Fi got it.
So 3.560 falls in here. That's in the general part of the band. Okay, so when general class licensees are not when general class licensees are not permitted to use the entire voice portion of a band, which portion of a voice segment is usually permitted?
Upper.
Upper.
Yep,
So
upper.
notice like up here on 20 meters, you have that exclusive section between 150 and 175 for extra. Believe it or not, 175 to 225 is for advanced. We still have some advanced operators out there.
When in doubt, use the uppers.
Yep. And the upper frequency is 225 to 350. Which of the following frequencies is within the general class portion of the 75 meter phone band? We look down here to 75 meters. Now, interesting, they call it 80 and 75. Anybody know why they call it 80 and 75?
Wavelength is in between.
No, because the wavelength, the band is so big, it's half a megahertz wide, and it's only at 4 megahertz, 3.5 to 4. Down here, it's 80 meters, and up here, it's 75. So it actually is big enough that there's not one particular name for it. So technically, I think it's called the 80 meter band, although a lot of people call it 75. So the 3900 falls in that blue section. Which of the following frequencies is in the general class portion of the 40 meter band in ITU region 2? Okay, so notice we have the blue band on the 40 meter band, 7.250. So the question is now, why do they need to say ITU region 2?
Good question.
Is of Hawaii.
Because you can get a ham license in Hawaii or Alaska, and
Okay.
they are not in ITU region 2. They are in a different ITU region, and And in some places that the US licenses hams, anything above 7,200 is not available. This is one of those bands that is not uniformly distributed around the world. Another one of those is 2 meters, believe it or not. Good opportunity to talk about that. Notice ours goes from 144 to 148. If you go to Europe, it's 144 to 146. They don't have the upper half.
Cut it in half.
Yep.
And what does ICU stand for?
Hmm?
ICU, what is that? mean?
ITU, International Telecommunications Union.
Oh, okay.
On the 20 meter band, what's in the 20 meter band? 14,225 to 350. So 14,305 falls in that band. What's inside the 15 meter band for generals? That would be, Gesundheit.
Bless you.
That would be 21.300. On 10 meters, basically general, extra, advanced, and general all have the same privileges, the entire band. And again, technicians and novices, believe it or not, can operate from 28 to 28.5. Okay. What portion of the 10 meter band is available for repeater use? Notice this section up here that says FM. Anything above 29.5 is available for repeater use. Typically 0.6 to 0.7 is repeater outputs. 0.5 to 0.6, I believe, is repeater inputs. So we had this discussion as to whether or not technician operators can use 10 meter repeaters. We recently had that discussion here. The answer is no, they can't, because even though they can get on 10 meters on the single sideband portion of the band, they're not allowed up here in the FM portion. When may a 10 meter repeater retransmit a 2 meter signal from a station that has a technician class control operator? Well, we just said that 10 meter repeaters, a technician cannot be there, right?
We can't do it.
You can, because nobody's transmitting illegally. Basically the repeater owner is taking the output of their repeater, which is being used by a tech, and moving it to this band. So even though the technician doesn't have privileges there, the technician did not put their signal there. So it's actually okay.
But you still couldn't have logged into the repeater yourself. It had to be the operator.
Wait, say the question again.
You couldn't have gone to the location itself. The operator of the beacon had to do it.
Well, it depends. I mean, let's draw this map. Excuse me. So here's a 2 meter repeater, and it's linked to a 10 meter repeater. So I am operating as a technician on the 2 meter side, and there is a back channel connection that takes the 2 meter audio and retransmits it on the 10 meter repeater. So long as the repeater owner has a general or above, that's actually okay.
So the answer was yes, okay.
Even if the technician that's using the 2 meter repeater suddenly has their voice pop up over here, they didn't put it there.
Right, okay, got it.
It may be strange to hear that.
Yeah.
You know, it's strange to hear that person there, but they didn't put it there. So it's okay. On which band is no phone operation permitted? That would be the 30 meter band. On which of the following bands is image transmission prohibited? That would also be the 30 meter band. Image would be also known as slow scan TV, which is transmitted over single sideband usually. 60 meters is an oddball band. 60 meters is a channelized band, and it's really the only one by law that's channelized. And the reason it's channelized is because we actually share it with the military. Someday we may actually have a continuously available frequency space like we do on virtually every other band. But for now, notice it says it's channelized. We have channel 1, 2, 3, 4, and 5. And weirdly, if you're going to use it, notice you have your USB tuning frequency and your data channel center. That really means that your data signal actually has to be centered in the middle of the band. It's a weird thing. But 60 meters is basically the one that's restricted to specific channels. When we are a secondary user on a band, such as, believe it or not, on the very large and popular 70 centimeter band, we're actually secondary to the military. Notice this says not available along Canadian corridor from 420 to 430. That's because Canadians are not primary there either. So we're not allowed to do anything that would interfere with them. Basically, if we are operating and somebody says that we are interfering with them, if we're secondary, we need to stop doing that because we're not primary. What's the appropriate action if on the 30 or 60 meter bands, a station in the primary service interferes with your contact? Again, on 30 meters is a wonderful band. It has a limit of 200 watts output. You don't have to fight against the big guns. There's no voice. It's all CW and data. It's a great band, but we're also secondary, which basically means sometimes you'll hear some really weird signals in that band. And it basically means if we hear a really weird signal in that band, we need to move off of that frequency to a different frequency because it's a shared frequency. The frequency allocations of ITU Region 2 apply to where we are in North and South America. Again, there are only 3 regions. There's 1, 2, and 3. I believe 1 is Asia and the Pacific, 2 is us, and 3 is the Eastern Hemisphere or Europe and Africa. Which of the following may apply in areas under FCC jurisdiction outside of Region 2? You might have different frequency allocations. You still have a US allocated license, but for instance, if you're in Guam, for instance, or American Samoa, you have different frequency allocations. I know when I was in Hawaii, if we look down at this band, at the 40 meter band, notice what you get from 7 to 7.1. Notice it's all red, right? Red is CW and data. But if you're in Hawaii, 7.088 lower sideband is where they do a lot of their afternoon nets. Because the rules are different there, because it's in a different part of the world. Okay, the maximum height above ground to which an antenna structure can be erected without notifying the FAA and putting lights on it is 200 feet. W3LPL, who lives in Maryland, who I lived fairly close to, is a very active member and has been for years and years of the Potomac Valley Radio Club. Had 7 towers on his property. 4 of them were 199 feet, 11 inches.
That's the way to do it.
Yep, 1 inch below the need to put up to tell the FAA about it and put lights on it. Because lights, if anyone has never done it, I've never done it. But what I've been told is that putting lights up on a tower, in addition to doing maintenance, is really expensive. Under what conditions are state and local governments permitted to regulate amateur radio antenna structures? Okay, so the rule is that amateur radio service communications have to be reasonably accommodated. This is something called PRB1. And regulations must constitute the minimum practical to accommodate a legitimate purpose of the state or local entity. Unfortunately, that is the state or local entity. And if you live in a homeowners association restricted community, that is a different thing because that's a private entity. And HOAs are great, except when they're not.
I got a question on that one, on one that I had read, where the gentleman did put up an antenna and the HOA came in and said, no, you got to take it down. And he did go to under the circumstances that he monitored for disaster relief in different countries, and it overrode that. Is that, I mean, that's about the only way you could get around
Pretty
it?
much, yeah.
Okay.
Either that or hide it. you know,
Yeah, well, he just left it up and just basically said, well, contact he contacted the
contact the
FCC, gave him the
contact the
paperwork.
FCC,
Yeah, and then all that did was piss him off. So,
right?
but he kept the antenna. Okay.
Yeah. Okay, which of the following is the purpose of a beacon? A beacon is something that goes beep, 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 transmits call sign, transmits location, power levels. The purpose of a beacon is that it's a one-way transmitter that's used by receiving stations to figure out what the propagation is like for propagation testing. The power limit for beacon stations, you are allowed to put up beacons. Beacon stations are limited to 100 watts PEP, which we did yesterday. PEP is peak envelope power. With which of the following conditions must beacon stations apply? There must be no more than one beacon signal transmitting in the same band from the same location. So if you have a mountaintop location, you can put up a 6-meter beacon, a 2-meter beacon, a 70 centimeter beacon, a 10-meter beacon, but you can't put up 2 for the same band. On what HF frequencies are automatically controlled beacons permitted? 28.2 and 28.3 megahertz. Those are 10-meter propagation beacons. Why should an amateur operator avoid transmitting on 14.1, 18.110, 21.150, 24.930, and 28.200? Those are magic frequencies because there are systems of propagation beacons set up all around the world that take turns. There are 18 of them in each location. There are 18 of them on each band that take turns operating and sending out signals for people to receive. So if you can copy the CW, you can figure out what areas we have propagation from in any part of the world just by going to that frequency and listening.
I did that last night and I could hear Japan and I could not hear New York.
Really? On what band?
The 1411.
Okay, that's actually not surprising because New York would be, the station, the one in New York would be too close. It'd skip right over you.
Oh.
Okay, which of the following transmissions is permitted? Retransmission of weather and propagation forecast information from U.S. government stations. Which of the following one-way transmissions are permitted? Anything that you're doing to assist the learning of Morse code. You can basically transmit practice bulletins and information bulletins and Morse code practice. When is it permissible to communicate with amateur stations in countries outside the areas administered by the FCC? Well, when the contact is with amateurs in any country except those where administrations have notified the ITU that they object. These are pretty rare. The United States actually does not have any other countries that have said we object. North Korea doesn't have any hams to worry about, so they don't object. There was a little something that happened a few years ago. Socotra Island off the coast of Yemen was activated by a bunch of Italians, and they were told by the Yemeni government as part of their licensing that even if they could hear them, they couldn't contact any Israeli stations because they were technically still at war. They could hear each other, but they couldn't contact each other. What are the restrictions of the use of abbreviations on procedural signals in the amateur service? They can be used if they don't obscure the meaning of the message. So the whole thing about encryption.
There's been a shooting in Oklahoma, 1 dead, 7 injured.
Jesus.
So why is that not surprising? Let's see. Let's see. Oh, procedural signals and abbreviations. So basically, you can use procedural signals and abbreviation. And the thing is that you are not allowed to obscure the meaning of a message. There's a lot of talk about what constitutes, codes and ciphers and things like that. We are allowed to, speak in any way we want. What we're not allowed to do is obscure meaning. And that doesn't mean, using something other than English. That means basically anything to obscure what's being said so that somebody won't understand it. You can't use a code that you've written between two people to obscure the meaning of what's happening. I mean, that's actually considered illegal. If you come up with a new digital protocol, you have to publicly document how the protocol works. Well, once you do that, and the decoding key is available to everybody free of charge, then it's okay. You can use it on the air. When choosing a transmitting frequency, ensure that the frequency and mode or the mode selected are within your class and privileges. Follow generally accepted band plans to agreed to, and monitor the frequency. And I would say also ask if the frequency is in use. That's a big part of monitoring the frequency. And who or what defines what good engineering and good amateur practice is per Part 97? This is kind of a giveaway. The fact that they mentioned Part 97, who wrote Part 97?
FCC.
FCC. So you have to follow the FCC rules.
Yep.
All right, so we are into transmitter power regulations and data emission standards. This is actually a little bit confusing, but really it's really not. What is the general power limit that we're allowed to transmit with?
1500.
1500 watts. Okay. So there are a couple of exceptions so what we'll bring up on the 30-meter band. Notice this says maximum power 200 watts. All right. So basically the rule is 1500 watts, except in certain cases. Notice that on 60 meters, it says max 100 watts ERP. Does anyone know what ERP is? ERP is effective radiated power. That takes into account gain as well. So if you have an antenna that has gain, you have to calculate that as part of your 100 watts maximum power. So that's another weirdness of the 60-meter band. Everywhere else, it's basically 1500 watts. If you are using an antenna other than a dipole, you must keep a record of the gain of your antenna accordingly on the 60-meter band. What measurement is specified by FCC rules that regulate maximum power output? 3 letters, PEP. And what does PEP stand for again? It's peak.
Peak envelope.
Big envelope power.
Peak envelope power. Okay. PEP is peak envelope power, which is basically the fact that you can't have an average power that's higher, right? If your average power is 1500 watts, it might be that your peak is 2500. So you need to have a peak envelope power, which is basically the most power that's coming out at any time, 2500 watts. Or sorry, 1500 watts. Which of the following limitations apply to transmitter power on every amateur band? The rule of thumb is you use the minimum power necessary to carry out desired communications. So the question is, why do we do that? And the answer is to avoid interference with other people who might want to be reusing the band. So if you only need 3 watts to get from point A to point B, you should probably only use 3 watts to get from point A to point B. If you're trying to be heard all over the world and you want 1500 watts and find that you need to use it, then you are allowed to use 1500 watts if the band permits it. Okay, so how many kilohertz wide is a sideband signal? 3 kilohertz. Okay. Well, except on the 60-meter band. The 60-meter band, being that weird one, has a maximum bandwidth permission of 2.8 kilohertz. Practically speaking, this is never really going to be a problem, but that's the rule, that the maximum bandwidth permitted is 2.8 kilohertz. Okay, this part is this part is where we get a little strange. We're talking about data rates. Okay, so data rates are such that information that is transmitted digitally takes as much room. The faster it's being sent, the more room it takes up. Certain bands have more space available. If you look at, for instance, the 40-meter band, there's only 300 kilohertz. If you look at the 70-centimeter band, we have 30 megahertz of space. 23-centimeter band, we have 60 megahertz of space, and so on and so forth. The world does not end at that point. In fact, if we were to look at this chart, we would see that there's a lot of different allocations out there. The amateur stuff is this nice little teal color. So there's the 80-meter band. There's the 6-meter band. And you would see that these little teal marks show up all over the place, as do lots of other things. There's an amateur station. There's an amateur right there. Notice it's at 2.4 gigahertz. There's another one right there. That's at 24 gigahertz. There's 200 megahertz of space up there. So the higher the frequency you go, the more space there is to transmit information. And the corresponding end result of that is that on lower frequencies, there's just not as much room. So the data rate is typically lower. So the maximum symbol rate permitted for RTTY or data emission below 28 megahertz. Below 28 megahertz would be 12, 15, 17, 20, etc. Because of the amount of space available, it's 300 baud. Yes, a blistering 300 baud, just like those old analog audio coupled modems where you'd plug your handset into the modem. On the 10-meter band, as we now get a little bit higher, you're actually allowed a blistering 1200 baud. Okay, so on the 2-meter band, because we have more space even, we're allowed 19.6 kilobaud, or 19.6 thousand thousand symbols per second. And on the 70-centimeter band, we are allowed 56 kilobaud, which is still kind of slow compared to today's world. I mean, you imagine if we were using a 56K modem right here, 56K modems to have this meeting. But that is what the bands allow because of the space available. All right, let's see. Volunteer examiners. Okay, so why is being a volunteer examiner included in this exam package?
For testing purposes and helping out.
Because a general can actually be a volunteer examiner.
Right.
A general can give exams to a technician class. That's right.
Yep.
All right. So volunteer examiners are accredited by a volunteer examiner coordinator. In order to, which of the following criteria must be met for a non-US citizen to be an accredited VE? The person must hold a US amateur radio license, general class or above. So if somebody wants to give US exams in Japan and you have 3 US licensed hams in Japan, they can give an exam in Japan. The minimum age to be a volunteer examiner is 18. What license examinations can you administer when you're an accredited VE holding a general class? You can administer a technician class license. Which of the following must a person have before they can be an administering VE for a technician class? You have to have a general class or a higher license, and you have to be accredited by VECs. VEC, again, is a volunteer examiner coordinator. So you have to have submitted all your certification information and probably taken a test and signed up to be a volunteer examiner and been accepted. Which of the following is a requirement for administering a technician class license exam? You need at least 3 VEs, general class or higher, to be present. A certificate a certificate of successful completion of examination is good for 365 days. Okay, so this is kind of an interesting throwback because, well, what license, what exam do you have to pass to get a technician these days?
Technician.
Technician. Okay, how about to get a general?
General.
Right. There's only 3 exams. Okay, but way back in the dark ages, there was a novice, a technician, a general, an advanced, and an extra.
Yeah.
And to pass a novice, you needed to do the written plus 5 words a minute code. To take it to a technician, you had to do a written plus 13. The general was a written plus 13, another written. An advanced was another written plus 13, and the extra was another written plus 20. So basically, let's say that you went in and you ran the table on your written exams and you didn't pass any code tests. What license did you get?
Nothing.
Nothing. Now, if you did that and then you passed your 5 words a minute, what license did you then get?
Marvelous.
Right, you got your novice exam. If you made it all the way through the general exam, for instance, or let's do this. Let's say that you went all the way from 0, you passed your novice test and your 5 words a minute test, and then you passed your 20 words a minute test. What license class would that give you? No, that would give you a novice because you haven't passed the written yet.
Oh, the written.
So there were a lot of reasons to have something called a CSCE, which was a
Yeah.
certificate for successful completion of examination. Now, the only reason to have that is, let's say you pass your technician, you hold a technician license, you pass your general, and for some reason the FCC is asleep for a week, right? And they didn't process the license. Well, you have this thing which says I passed my general, and that basically allows me to sign /AG, give your call sign /AG when transmitting somewhere that requires you to have general class privileges. It used to be that this certificate was good and still is for 365 days. But the reason that it was so important was, let's say like me, I passed my 20 word a minute test and I had never passed anything beyond the novice. I then spent 1, 2, 3, 4 months passing my written exams. I've similarly given exams to people who had passed they passed all their written exams and 5 words a minute, which basically meant they had all this credit for having passed written exams, but didn't have the code to match it. So then they had 365 days to get as many code tests as they could before having to retake the written exams. So it's good for 365 days, not 1 year. It's good for 365 days. On which of the following band segments can you operate if you're a technician and have a certificate of successful completion of examination for a general? Well, you can operate on your old general class areas. You can operate on the new general, on the old tech class areas, or you can operate in a new general class area. Again, signing /AG. And in fact, that's the next question. When must you add the special identifier alpha golf or AG? And that's if you are using privileges that are conveyed by your certificate and your license is not in the FCC database yet.
Good question, Scott.
Yep.
One of them is, I made it more a comment than anything else, but back when Jesus was a baby, if you didn't pass your code, you didn't get a chance to take the written. And that was in the mid-60s.
Did you go to the FCC office?
I went to some office in downtown Denver. I don't know whose it was.
No, it was the FCC.
Okay.
It was the Federal Candy Company.
Okay. That happened a long time ago.
Yeah, it did.
One of the reasons I never took it beyond that.
Yep.
The second one is I've got a book, which is supposedly a general class study guide. And I ran across a statement in there that said, if you can prove that you have a technician license that was issued before 1987,
yep,
you don't have to take the general exam. Never heard that.
That may very well be true. Because the
I'm
general,
suspecting that the technician license written was the general written, but it didn't have the code to it.
I believe that's true. Let me see, FCC.
I'm still trying to track down when my license was issued, and I've got a few more things to fix, but so far I haven't gotten to a place that tells me what happened before the new time it was renewed the last time.
Okay, let's see. Let me share it. Here we go. What must persons who submit documentation of having held an expired technician license issued before 3/21/1987 will be granted element 3 credit upon passing the element 2 exam and appearing as an active licensee in the FCC database. And thus will be granted general privileges. Now,
All right.
but you're listed as what? Your call sign is WB7UMK.
Correct.
Okay. And did you retake it or have you always had it?
I've always had it.
So, okay, so it's not expired and it's never
No.
expired?
Nope. I just don't know when I got it. And I've got some places I went to look, like, was it QRS or something, and AAR or ARRL, and the FCC, and FCC booted it off to somebody else. I did get an email this morning from somebody at ARRL that says, here's the, I don't know what it is, here's the code books, or here's the, I think back then they were listing the people who got licenses at certain times. I just haven't had time to wade through that. We don't need to take time on this show to figure it out. I just was curious.
This actually may be of some interest. What I'm going to do is share this, and actually there is a let's see, great place to do this. Let's share this. Okay, so there's your QRZ entry,
right?
Which could use a little bit of updating. Could use a little bit of updating. Here's the data.
Right.
Right. Okay, but there's also the internet. Come on. Archive. Radio call books. Have you been through here?
That's the one I got this morning from ARRL.
Which, by the way, I should throw out there, if you're not a member of ARRL, it's a really good idea to join.
Okay. Yeah, that's the page I saw. I didn't have time to jump into it.
So when do you think you got it with a WB7? Let's see, when?
WB7 UMK. When were cars invented?
Well, let's see, when were WB7 calls issued?
Oh, there you go.
1965 to 1975.
No screaming weenies.
Oh, I don't know. Does it say that?
I don't know.
But 1965 to 1975. So
I didn't think I got it that early. But
it sounds like it was. I would have guessed it was a while ago.
Okay.
Let's see. Go to more. And let's go to, let's say, 1972. Let's just pick a year.
Yeah, that.
And winter 1972, radio amateur call book, United States. Actually, I found out using this method that my daughter, who holds the call sign W7HER, has a call sign that was held by somebody who was her name is Marjorie Ramey. And she actually, my daughter goes to the University of Oregon. Marjorie Ramey worked at the University of Oregon in housing. Not only that, she's 96 years old and she's still alive. And we actually, she lives a mile from campus and we went and met her.
I'll be darned.
Okay, let's see. Okay, what's it called again? WB7. UMK, right?
Whiskey Brocker Bravo 7 Uniform Mike King.
Okay, so let's go and see. It's going to be on this page, maybe. And let's go zoom in. No, this is actually a really good use of time, I think.
Well, I hope everybody else isn't bored.
My apologies to everybody if you don't think this is interesting.
No, it's very interesting.
I'm waiting for you to find it. I'm excited.
I am too. Well, what I'm trying to figure out is how I can zoom. There we go. WB7, oh, it's got to be on the previous page if it's there. Come on, this is getting in the way. There we go.
I like hunting for gold.
WN7UMK. Okay, so. All right, so maybe they hadn't gotten to the WB7s yet, so we got to pick another year. All right, well, we'll go
I'll
down.
go through that, but why couldn't you search in the upper right corner? Or
Oh, I probably could. I just want to,
don't mess with it now.
I want to do one more. Here we go. We'll go
Okay.
1976. We'll go one more.
Yeah. I vote for you to find it.
Well,
Yeah.
is 70, for example, is 76 everything that was in effect at that point in time,
Yeah,
or only
yes.
those that were released like in
Any,
70?
anything that was in effect,
Okay, that's
all
even
active licenses.
better yet.
Yeah. Okay, so let's zoom in. We got W's. We got Victor's. Uniform Mike. Okay, well, it's not showing up there. So let's,
All right.
I would say then then we would go into starting in the early 80s and see what it got for there.
Yeah, I'll do that. You don't have to drag everybody else through it. I'll
Okay.
do that. If I
Anyway.
have any, can't get it, I know how to send you an email.
Yep. And I've actually found lots of other information like this. Like I'm also the technical advisor for the University of Oregon Club. And I found an evidence of the U of O having a station back in 1922.
Good.
Hey, did you pull that site up one more time for us?
Let's see, there it is. Here, I'll hop back to right there. Here, I'll put a link out there too.
Archive.org search.
Yep, I'll copy that and stick it in the chat.
All right, thank you.
There we go.
Yeah, my guess is that, well, mid to late 70s would not be out of the question. But
Yeah.
anyway, I'll check it out.
I'm going to do one more. I'll look up 83. Okay, it's quick enough and easy enough to do. Here we go. Go. And let's look up the 7s. And we'll go, oh, there were a lot of new 7s then. This is actually quite, this looks quite good. Okay, UT, UK. All right, even picked the right page. Okay, UMK. WB7 UMK.
That would be me, and that
There we
would be the
go.
location.
Yep.
And so what the date was
It was
this
the
is
80. It was the 83 call book. 1983.
okay. Doesn't say when it was issued, it just says it's there.
Yep, it was active.
That's all I need to know.
Yep.
I'll be damned.
God, you're a winner.
Yep.
Well, I just,
There you go.
I'm very happy to get the 6 hours of education here. I'd still be happy to take the test and so forth, but it just blows me away. I mean, Christ, at 80 years old, trying to remember what happened back then.
Yeah.
I'm kind of like, which car was I driving and did I have a radio in it?
That was very cool. Thanks.
Yeah. And the other cool thing is that anybody can do that. All the call books are there from all the way back to the 19-teens.
Jeez.
It looked very different back then. The FCC didn't even exist. Okay.
Actually, I'll share with the group more than you want to know, and I'll try to keep it to like 3 sentences. But my father, who died 20 years ago at 93, grew up in the 1920s, and he was a big radio buff because that was high technician at the time, high technical. But he never got into ham. And he'd always wanted to. And so the big deal was when I was graduating from college in the mid 60s, he wanted us to both get our licenses. And by and large, I mean, all the written stuff I'd had in school, that was a no brainer. But I couldn't master the code and he couldn't master the code. So we never got our licenses. And then the technician came along because I came upon a fatal accident on Wolf Creek Pass in Colorado in a vehicle that had only a CB radio in it. And obviously we couldn't get hold of anybody. So that prompted the getting the technician license. Anyway, here endeth the story.
Well, it's interesting. I actually, the code hasn't been required to get a license for 20 years now or so.
Yeah.
And what people are finding, so even now, is that now that the concern was that you take the code away and it'll the people who come into ham radio will be different somehow, and it'll be the death of the code.
Yeah.
Well, what's actually happened is that people now, they get into ham radio and they're the same people who were always interested, but now a lot of them want to learn Morse code because it works in the absence of a lot of other modes that don't work.
And it makes sense. If you didn't have the pressure to pass it, you'd
That's
spend
right.
some time playing with it.
That's right. And I didn't actually learn to enjoy it until I started having fun with it,
Well, given Oregon won't let you use your cell phone in the car, how do you get away with keying on a keypad?
Well, I haven't done that in a long time.
It's on the
All right,
seat next to you.
What's
Yeah,
the
I have-
requirement?
Thanks for indulging me.
Yeah,
There should be a requirement for Eagle Scout that you had to know Morse code.
that's true.
Yep.
All right, here we go. Continuing. Who may receive partial credit for elements represented by an expired amateur radio license? That's anyone who can demonstrate that they once held an FCC General, Advanced, or Amateur Extra license that was not revoked. So you need to go back and talk to them about it and see what it's good for. What's required to obtain a new general class license after a previously held license has expired and the 2-year grace period has expired? Let's say you had an extra, you let it expire. If you can pass the technician exam and show that you had it, you can get it back.
Okay.
What types of messages for a third party in another country can be transmitted by an amateur station, since you're going to be doing DX a little bit more maybe? Only messages relating to amateur radio or remarks of a personal character, or messages relating to emergencies or disaster relief. So basically, I can have somebody in a country that permits third-party operation. So for instance, like between the US and let's say Costa Rica, if I'm a ham here and someone's a ham in Costa Rica, we can each have a non-licensed person say, come up to our microphones and say hi to each other. If some countries, in particular Europe and Japan, they don't allow third-party operation, and that goes back to the days when the telecom companies in those countries were owned by the government. So that would basically sidestep the government's ability to receive funds for using their long distance services. So they didn't allow third party for doing things like that. Which of the following would disqualify a third party from participating? The third party's amateur license has been revoked and not reinstated. So that's really the only reason why somebody couldn't be a third party, if they used to be a ham and their license was revoked. Which of the following conditions require an amateur radio operator to take specific steps to avoid harmful interference? If you live within 1 mile of an FCC monitoring station, you're not allowed to operate. If you're in a band where the amateur service is secondary, you can't interfere with anyone. And when transmitting spread spectrum emissions, believe it or not, we're allowed to do spread spectrum. You have to make sure that your spread spectrum operation doesn't splatter all over the place and cause interference. On what band may automatically controlled stations transmitting RTTY or data emissions communicate with other automatically controlled data stations? That's anywhere in the 6 meter or shorter wavelength bands, and it's limited to some segments of the HF bands. So basically an automatic station communicating with another automatic station. Doesn't sound like a lot of fun, does it? What's required to conduct communications with a digital station operating under automatic control outside the automatic control band segments? So that means that the station initiating the contact must be under local or remote control. There's 3 different modes of operation: local and remote. Local means you're actually at the keyboard. Remote means you're connecting to it over the internet and controlling it. Automatic means automatic. It's handling everything by itself. You know, there's a computer running it and it's handling it itself. Okay, so we do share the 13 centimeter band, which doesn't even show up on that chart. So the 13 centimeter band is the next band up above 23 centimeters. It is also known as 2.4 gigahertz or the Wi-Fi band. Even though we share several channels with the Wi-Fi band, you know, Wi-Fi like Wi-Fi on your computer or on your phone, we are not allowed to intercommunicate between the two. So we're not allowed to talk to the Wi-Fi stations at all. For spread spectrum communications, essentially literally spread spectrum, it's a different mode of talking. We're allowed to transmit with a power of 10 watts. And when are we allowed to, let's see, under what circumstances are messages that are sent via digital modes exempt from Part 97 third-party rules? And the answer is never. So basically there's that thing essentially saying you always have to follow the rules. Unless, of course, it's an emergency and then you can not follow the rules, but that's in the rules, which means that emergency operation is still following the rules.
The question is does spread spectrum mean frequency hopping of a given message?
It actually does.
Okay, that was
Yes.
my question.
Yeah, spread spectrum is actually like spread spectrum communication.
Okay.
It's a
Trunking?
Hmm?
Is that like trunking?
something like that. Yeah, we're actually allowed to do a format of it.
I got a little war story to share with the group I think might be interesting. My next door neighbor here in Beaverton, Wyoming, fellow about my age, was wounded in Vietnam in about 1967. And when he was air-evac'd to the hospital, they had mixed up a couple of numbers. And the other guy in his platoon who was killed was reported as wounded, and Tony was reported as killed. So he got to the hospital and he said, "What are you doing here? You're supposed to be dead." Now then he went bonkers because he had these visions of back in New York, a couple of uniformed, officers showing up at his house, scaring the hell out of his mother. So using Mars and amateur radio, they set up a hot link from the hospital in Vietnam to Hawaii to Chicago, and then a landline at home. And he got to talk to his mother live over that link to tell her that
He wasn't dead.
don't believe anything if somebody says I'm not okay, because I'm okay.
I'm not dead.
Yeah. And then she says, "What do you mean you're not dead? I thought you had a desk job." Well, hell, everybody told us we had a desk job. We didn't tell anybody that there was a combat exposure.
Whoops.
Yeah. Tony still gets teary-eyed when he tells that story.
Well, that's the end of the book. Let's what we haven't gotten to do is if anybody wants to take the mic and introduce themselves, that would be okay.
Hey, Scott, I've
Yeah.
got one question.
Yeah.
Could you go back to that gentleman's website? I think it was Tom. And
Oh, NS6T. Yeah.
yeah, appreciate that. And put that link on the chat for me. And I'll take the stage since I'm here. My name is Eric Van Zandt. Sorry about that. That's my dog. I live in Canby, Oregon, and been a tech now for about 10 years. and do search and rescue and looking to upgrade to general.
Cool. So do you have an exam scheduled or planned?
No, not yet. I'm just starting them. This is the start of the homework process.
Oh, good.
And thank you for the class. It was
Yeah.
very, very good.
I know it's
Yeah,
a
I
lot of
would-
material.
I would tell you, thank you. That was very, very good. I certainly will remember everything it said, but I would never remember everything I've read. That's
Yeah,
no
okay.
good. Yeah. We just moved up to Oregon really around November 1st from 50 some odd years in Arizona. And we've kind of been blamed to be reverse snowbirds, but that's beside the point. I live in an over 55 community north of Beaverton, which is in Washington County. And there's 560 homes. And they have a very, very active, what I will call civil defense unit. Now, they kind of patterned it around the Great Shake, the fact that we're sitting on a fault line and the earthquake is many, many, many years overdue. But they are set up a pretty active outfit to figure out, should something happen, a community catastrophe, how to check on every house, how to get medical care, how to be self-contained, basically how to live if we can't get any outside help for 2 weeks. And that kind of inspired me to go from technician into getting my general, to work with some of the people who are doing the radio communications and that deal. End of sermon. You all have a good time.
Anyone else want to go?
There's a coffee mug that I just got from some friends as I got my technician license. It says ham radio. It's not a hobby. It's a survival skill.
Yeah.
That's good, Marilyn.
No, I'm here in Eugene with Scott, Santa Clara area. I've had tech for 11 months now. And I just got hooked after I retired. And it's just a lot of fun, but hearing Scott, and especially Scott, a lot of information there. That's how I got interested in it, but I want to upgrade to where I can, get out there a little bit more on different frequencies. I'm really used to that. In fact, I talked to you, Scott, about maybe, you offered up to come out and look at what you had and see some things. And it's just really interesting to me, but hopefully I'm going to keep going and get an extra. But I want to get my general first.
Yeah.
I want to thank you as well. Robert Albino recommended me to your courses.
Oh, Robert. How do you know Robert?
Well, we have a history together of meeting at the Oregon Country Fair of all places.
Okay. Do you guys do Morris dance too?
No, I'm sorry. The question was,
do you do the Morris dance thing also?
Oh no, that's his wife Kathleen, who's a brain surgeon.
Yeah, I know.
No, but he saw that I used to teach at Police Academy for 10 years, amongst other things. And he saw that I have this amazing scanning station where I monitor the OSP frequencies. And he said, Mark, it's just a natural for you to go into this. And so that's when I took your technician's class, and now I'll get the general. By the way, Kathleen has a general too, which I just find amazing.
Mm-hmm. And she's a brain surgeon.
Yeah, just as a hobby.
Yeah.
Yeah.
Anyway, I want to thank you. I'm going to sign off now and appreciate all of you guys. Fantastic.
Good job.
Good to meet you.
Thank you.
And lastly, Scott, Jerry Harris, who I think is an extra K7 JPF, is a fellow who recommended me to take this. He's kind of the head radio guy of this community civil defense thing.
Okay, cool. I didn't know
Scott?
anybody knew who I was. Yeah.
This is Janet. I'm in Oklahoma,
Yep.
and
Hi,
I
Janet.
took your class at Thanksgiving.
Yep.
At Thanksgiving, and took my technician test that weekend, and so getting ready to take my general. So this is the beginning of the study program. So,
Cool.
But I thank you for your time this weekend. I've really enjoyed your class and listening to everybody's comments. It's really been fun.
It's fun. It's funny because the general class is very different from the technician class because, everyone's already got their license. So everyone's sort of on like at least a common plane already.
We
So-
actually knew a little bit of something.
Well, exactly.
Oh.
Scott, Dwayne Sherman.
Hey, Dwayne.
Okay, I'm new to the ham radio operator. I started about a year ago, but excuse me. I'm also a millwright. I was a millwright at the nuclear power plants in Denver, Colorado,
Okay.
and so had a lot of fun there. And that was one of the more interesting plants around. It was a gas cooled. And the reactor, so there wasn't any water in there, and the heat was helium was a noble gas that we transferred our heat with, so it didn't go through the pipes like water doesn't get on the outside of the pipes, and so we actually decommissioned the plant, rubbed everything down and got it clean, and they're the first ones to return their NRC license back to the government for their nuclear power plant. It was the guy that had the highest radiation on the site was the gardener, and he was out in the sunlight doing the lawns and everything. And it was a clean plant. You could decontaminate everything, and it's back to still operating, still making electricity as using gas turbines as the heat source now. So it was interesting, but now I'm out here and playing on trying to figure out how to. I'm also in the part of the Lane County medical alert system here. So once a week I get on the net and we talk through the repeaters to all of the different medical facilities in the whole state of Oregon, checking out our radio communications every week. So that's been a real interesting time. So okay, I'm out of here.
Dwayne, what city in Colorado is that plant close to?
That was up at Platteville, just north of Denver, about 50 miles.
Got it. Yeah, I went to school at Boulder. Thank
Yeah,
you.
straight east of Boulder.
How big of a plant?
That was a 350 megawatt plant.
Okay, big enough for a few things.
Yeah. It and the operation of the system was that if you the rods and everything were lifted up and then by a cable, and then each one of these cables had a magnetic brake on it, so it would grab a hold of the cable and hold it up so that the reactor could be active below it. And so if you ever lost power to the plant, say somebody came in and tried to attack the plant, and the second it lost power, the magnets would let go, and gravity has never failed, and so all of the rods would go in. And and if the pressure was differential, we had these thick carbon discs that were about 4 inches thick that they would only take about 20 pounds differential to break through. And so if the pressure internal to the operation and the external weren't maintained in that band, then these things would do, and all these marbles were about the size of a regular marble, would all flow down in there, and they were neutron sponges. They were so again, that would shut it down. There was no matter what happened, all you relied on was gravity.
Well, I've always I've always been fascinated by the whole concept of xenon poisoning in a reactor. And I don't know. I think that might be, specific to a uranium reactor or something, but I know that the part of the fission products can actually, like you were saying about xenon sponges, like xenon doing that to a reactor can basically, knock it down and out of commission for 36 hours or so. But
this was fantastic. That was the best job I've ever had in my life.
Well, you know what amazed me, and we didn't even know it. When I was at the University of Maryland, we actually had a research reactor right across the street from the engineering building.
Yeah.
It was a little reactor, but it was a reactor. I mean, they had to have inspections, and we had a whole bunch of nuclear engineers on campus, and they would glow at night, and
You knew where they were.
yeah, exactly.
Hey, Scott.
Yeah.
Real quick. Sorry to interrupt. How is this going to be accessible online?
Well, as soon as I can stop recording. There, I'll stop recording.